Within the massive cosmos, there are regions where galaxies cluster together in dazzling cities of light, and then there are places like the Bhuta's Void. Stretching nearly 1 billion light-years across, this immense cosmic hollow is one of the largest known voids in the observable universe. It has been called the Great Nothing, a staggering gulf where, by all expectations, countless galaxies should be shining, yet only a scarce few can be found. What could carve out such an enormous emptiness? Is it merely a natural quirk of cosmic structure, or could something far stranger be hidden within its darkness? Before we delve into what lies inside the Bhuta's Void, we would appreciate if you could like the video and comment below where you're watching from and what time it is for you. Now, settle in for a fascinating journey to the centre of this mysterious void. The name alone feels mysterious, like something drawn from an ancient myth or a tale whispered by stargazers of old. Yet it is not a story or a legend. It is real, it is vast, and it stretches across the cosmos as one of the strangest features ever discovered in the universe. When astronomers talk about it, they describe a place that seems almost impossible. A massive region of space that looks nearly empty. A yawning chasm of darkness where there should have been countless galaxies. It is not simply an ordinary gap, it is one of the largest known voids in the universe, so huge that even the human imagination struggles to grasp its immensity. The very existence of the Bhuta's Void has fascinated scientists, stirred the curiosity of the public, and raised profound questions about how the universe is structured. Why does such emptiness exist? What does it mean for our understanding of the cosmos? And, in the quiet corners of speculation, some even wonder, could something entirely unknown dwell within that cosmic darkness? To understand why the Bhuta's Void is so captivating, one must first picture what astronomers expect when they peer into the universe. Normally, when telescopes sweep across the heavens, their lenses and sensors capture galaxies by the millions. These galaxies are not evenly scattered, but they tend to cluster together into cosmic filaments, vast webs of light and matter that stretch across space like glowing threads. Between these filaments lie voids, the dark gaps where galaxies are sparse. Astronomers have long known that the universe is like a sponge on a cosmic scale, bright filaments and clusters of galaxies forming the solid structure, with pockets of emptiness in between. But even in these empty spaces, one still expects to find galaxies here and there. The voids are not truly void, they are just thinner regions. Yet when astronomers discovered the Bhuta's Void, what they found stunned them. This was no ordinary empty pocket. This was a staggering desert in the sea of stars, a space so barren that it seemed unnatural. Discovered in the year 1981 by astronomer Robert Kirshner and his team, the Bhuta's Void was found in the direction of the constellation Boötes, a region of the night sky known to stargazers since ancient times. Boötes itself is easy to spot, for it contains the bright star Arcturus, one of the most luminous stars visible to the naked eye. But behind this familiar constellation lies a secret that the human eye could never detect, an emptiness spanning roughly 330 million light-years across. To put that number into perspective, light travels at nearly 300,000 kilometers per second, and even at that blistering speed, it would take light 330 million years just to cross from one end of the Bhuta's Void to the other. This means that the void is so vast it could contain many thousands of Milky Way-sized galaxies within it, yet only a few dozen have been found. Imagine expecting a bustling metropolis and finding only a tiny cluster of lonely villages. That is the scale of the mystery. The discovery of such a massive void was not just a curiosity, it shook the way astronomers thought about the large-scale structure of the cosmos. Scientists had already been mapping galaxies and noticing patterns of clustering, but the Bhuta's Void seemed extreme. How could such an enormous volume of space be so empty? Was it a natural result of cosmic evolution? Or did it hint at some unknown mechanism at work? Some researchers even half-joked that if one wanted to hide an alien civilization, this would be the perfect place. So far away, so dark, so sparse that it would be beyond ordinary detection. Others speculated more cautiously, wondering if the void was simply the result of gravitational dynamics over billions of years, where matter naturally pooled into filaments and left behind regions of near emptiness. Regardless of the theories, the fascination grew. The Bhuta's void became a cosmic riddle, one that continues to intrigue scientists and capture the imagination of the public. Part of the allure of the Bhuta's void lies in the human response to emptiness. As a species, we are drawn to mysteries, and nothing is more mysterious than a silence that feels unnatural. Standing in a forest, one expects to hear the rustle of leaves, the call of birds, the hum of insects. If all falls quiet, the silence itself feels louder than any sound. The same is true with the universe. We expect to look into space and see the flicker of countless galaxies, the distant glow of star clusters, the soft haze of nebulae, when instead we see a great hollow, a cosmic silence. It feels eerie. The absence of galaxies becomes as powerful as their presence. It is like staring into a cosmic abyss that dares us to ask, why? Astronomers, of course, approach the Bhuta's void with the tools of science. They measure its size, estimate its contents, and try to fit it into the broader pattern of cosmic structure. But even for them, there is a sense of awe. The void is not merely large, it is staggeringly disproportionate. Its diameter of over 300 million light-years makes it one of the largest voids ever detected, occupying a volume of space so massive that it defies easy comparison. If our Milky Way galaxy were placed inside the void, it would look like a single grain of dust floating in a cathedral-sized hall. Even our local group of galaxies, the Milky Way, Andromeda, and their smaller companions, would be utterly insignificant against the backdrop of such a gulf. Astronomers sometimes call the Bhuta's void the Great Nothing, a title that perfectly captures both its scale and its haunting nature. The public, too, has found itself mesmerized by the Bhuta's void, though often for different reasons. For those who are not trained in astrophysics, the void sparks the imagination in ways that science alone cannot contain. Some see it as a terrifying abyss, a symbol of how small and fragile humanity is in the grand scheme of the cosmos. Others see it as a canvas for speculation, perhaps a place where hidden phenomena exist, undetected by our instruments. Stories and theories have sprung up, some grounded in science, others venturing into the realm of science fiction. Could the void be evidence of something artificial, as though some unimaginable force had cleared it out? Could it hide civilizations so advanced that they leave no trace? Or is it simply the universe reminding us of its vastness, its strangeness, and its indifference to our expectations? The fascination with the Bhuta's void is also tied to the way humans grapple with the concept of nothingness. On Earth, true nothingness is rare. Even in deserts, even in deep caves, life finds a way to fill the void. But in space, emptiness is common, and yet even there, galaxies and stars usually break up the darkness. The Bhuta's void stands as an extreme, an emptiness that feels almost too much to accept. When people hear the phrase 300 million light-years, their minds struggle to picture it. It is not just large, it is beyond scale, beyond comprehension. The brain, accustomed to thinking in kilometers or miles, cannot truly hold such distances, and so the void takes on an almost mythic quality, a symbol of the limits of human understanding. In that sense, it is not only a scientific puzzle, but also a philosophical one. It confronts us with the vastness of existence and asks us what it means to find so little in so much. When scientists study the Bhuta's void, they do so by counting the galaxies within it. The number is startlingly small. Only about 60 galaxies where one might have expected thousands. That scarcity alone makes the void remarkable. It is not completely empty, but it is far emptier than theory would predict. The galaxies that are there seem lonely, drifting in an ocean of darkness without many neighbours. In most of the universe, galaxies interact, pulling on each other with gravity, colliding, merging, stirring up bursts of new star formation. But in the Bhuta's void, such interactions are rare. One wonders what life, if it exists in those galaxies, would think of their surroundings. Would their night skies seem darker, their view of the cosmos lonelier compared to ours? These are speculative thoughts, of course, but they add to the human fascination with the void. It is not just a feature of astronomy. It is a canvas upon which we project our curiosity, our fears, and our longing to understand the universe. The Bhuta's void also plays into the age-old human theme of confronting the unknown. Throughout history, explorers have set sail into uncharted seas, climbed mountains or plunged into caves, driven by curiosity and courage. Each time, the unknown was both terrifying and thrilling. The Bhuta's Void is like one of those frontiers, but on a scale that dwarfs anything on Earth. It is an uncharted sea of darkness, not to be crossed by ships or footsteps, but by the probing eyes of telescopes and the models of astrophysicists. And like all frontiers, it challenges us. It asks whether we are content with what we know or whether we will push further into the unknown, seeking answers even when the scale seems overwhelming. The void has sometimes been painted as a place of hidden menace or great beauty. To some, it is the ultimate symbol of cosmic horror. The idea that in the great silence of the universe, there are gulfs so immense and so empty that they remind us how fragile we are. To others, it is beautiful precisely because it is so strange, a reminder that the universe is far richer and more varied than our imaginations alone could invent. Either way, the Bhuta's Void captures something deep within the human spirit, the desire to confront mystery, even when that mystery takes the form of absence rather than presence. Astronomers continue to study the Bhuta's Void, trying to place it within the grand tapestry of cosmic structure. The prevailing view is that it formed naturally as galaxies clustered into filaments, leaving behind great hollows. And as telescopes grow more powerful, scientists will no doubt uncover more about its contents, mapping its galaxies in greater detail, perhaps even finding faint galaxies that were missed before. Yet even if every galaxy within it were catalogued, the void would remain extraordinary. Its size and emptiness are beyond dispute, and they ensure that it will always hold a special place in both science and imagination. The discovery of the Bhuta's Void begins in a time when the universe was still being mapped in ways that would seem slow and painstaking by today's standards, but which were revolutionary and groundbreaking for the early 1980s. In that era, the tools of astronomers were both remarkable and limited, a mixture of painstaking observation, careful recording, and ingenious deduction. The sky had long fascinated humanity, but understanding the large-scale structure of the cosmos, how galaxies, clusters, and emptiness were distributed across unimaginable distances, was only beginning to take shape. The Bhuta's Void, one of the most astonishing and puzzling discoveries of modern astronomy, emerged from this delicate and meticulous work, revealing a void so vast and so utterly empty that it seemed almost to challenge the very imagination of scientists who first glimpsed it. The first identification of what would later be called the Bhuta's Void took place in the early 1980s, during a period when astronomers were beginning to understand that the universe was not a random scattering of stars and galaxies, but had a structure, a sort of cosmic web. To achieve this, they employed a methodical process that involved mapping galaxies in 3 dimensions, rather than merely noting their positions in the night sky as points of light. At that time, the primary way to gauge distance was through measuring what is called redshift. Light from distant galaxies shifts toward the red end of the spectrum as the universe expands, and the amount of this redshift provides a measure of how far away the galaxy is. By measuring the redshift of hundreds, and eventually thousands of galaxies, astronomers could construct 3-dimensional maps of the universe on scales never before attempted. It was in this context that the Bhuta's Void emerged from the data. Astronomers were conducting a survey known as the Galaxy Redshift Survey, a painstaking program of observing the light from distant galaxies, measuring the spectrum, and calculating their redshifts. In 1981, 2 astronomers, Robert Kirshner and his colleagues, began analysing the results of one such survey. They were particularly focused on the large-scale distribution of galaxies in a specific region of the northern sky, an area that came to be associated with the constellation Bhuta's, a name which means herdsman in ancient Greek. As they charted the positions of galaxies in this region, a startling pattern began to emerge. Unlike the expected relatively uniform spread, they noticed a massive expanse where almost no galaxies seemed to exist. This void was enormous, far exceeding the sizes of previously known empty spaces between galaxy clusters. Initial calculations suggested that the region spanned roughly 250 million light-years across. To put this into perspective, our own Milky Way galaxy is about 100,000 light-years in diameter. This means that the Bhuta's Void was 2,500 times larger than the span of our galaxy, a scale that is almost beyond human comprehension. The emptiness was so extreme that when they compared it to the number of galaxies expected based on surveys of other regions, it seemed to be missing perhaps several thousand galaxies. In an age when computers were far less powerful than today, analysing this kind of data required immense patience and care. Each measurement had to be verified, every anomaly double-checked. The possibility of observational error was a real concern. Could it be that the void was simply an artifact of incomplete data, or a result of the limitations of the telescopes used? To address these concerns, astronomers employed multiple methods. They cross-referenced their findings with different telescopes and different surveys. The surveys were conducted using wide-field optical telescopes capable of capturing large swathes of the sky in detail. In addition, spectrographs, instruments that dispersed light into its component colours, were crucial for determining the redshift of each galaxy. By systematically collecting the spectra of galaxies across this region, astronomers could calculate distances and construct a three-dimensional map. The meticulous work required patience, as each galaxy's light had to be carefully observed, measured, and recorded. Over time, as more and more data accumulated, the void's presence became undeniable. The region that had once seemed perhaps an observational fluke now appeared to be a genuine cosmic feature, a vast expanse of emptiness stretching for hundreds of millions of light-years. The discovery of the Buta's void did more than merely reveal an empty region of space. It challenged astronomers' understanding of the large-scale structure of the universe. Until then, the prevailing view was that the universe, while clumpy on small scales, would be relatively uniform when considered on larger scales. Clusters of galaxies, superclusters, and filaments were recognized, but a void of this magnitude was almost unthinkable. The existence of the Buta's void suggested that the universe had an even more complex structure than previously imagined, a cosmic web of matter and emptiness interwoven on a scale that dwarfed entire clusters of galaxies. As the 1980s progressed, additional surveys helped confirm and refine the details of the Buta's void. Astronomers continued to measure the positions and redshifts of galaxies surrounding it, and they discovered that the void was not completely empty. There were, in fact, a few scattered galaxies within its expanse, sometimes called void galaxies, which appeared isolated and strangely detached from the more densely populated regions. These galaxies were of particular interest because they provided insights into how galaxies could form and evolve in environments with so little matter nearby. The contrast between the emptiness of the void and the relative abundance of matter in surrounding regions highlighted the extraordinary scale and variety of cosmic structures. The methods used to study the Buta's void also illustrated the gradual evolution of astronomical techniques in the late 20th century. Early redshift surveys were painstaking and time-consuming, relying on long hours of observation and careful manual analysis. Each spectrum was carefully measured, often requiring photographic plates or early digital detectors to record faint signals. The advent of more advanced electronic detectors, computer-assisted analysis, and automated cataloguing would later accelerate the pace of discovery, but in the 1980s, the work was deliberate and meticulous. Astronomers often had to make repeated observations to ensure accuracy, comparing results from different nights and different instruments. The discovery of such a massive void in the process was both a triumph of careful observation and a testament to human perseverance in the face of cosmic vastness. The identification of the Buta's void also sparked debates and theories about how such a vast emptiness could exist. Was it a product of the early universe, a remnant of the primordial fluctuations that led to the formation of galaxies and clusters? Or could it have formed through the merging of smaller voids, gradually growing into a single immense expanse? These questions prompted further surveys and theoretical work, encouraging astronomers to consider not just the presence of matter, but also the distribution of the unseen, dark matter that dominates the universe's mass. Although the void appeared empty to telescopes observing visible light, astronomers speculated about the presence of diffuse gas, dark matter, or even faint undetected dwarf galaxies. Each of these possibilities required careful modelling and continued observation, expanding the horizons of cosmological research. By the end of the 1980s, the Buta's void had become a landmark discovery in astronomy, widely discussed in scientific journals and popular science publications alike. It was a symbol of the vastness and strangeness of the cosmos, a reminder that even in regions where light and matter were scarce, the universe was teeming with mysteries. The methods used to identify it, meticulous redshift surveys, careful mapping of galaxy distributions and cross-referencing multiple observations, would serve as a model for subsequent studies of large-scale cosmic structures. Researchers realized that the universe was not a uniform expanse, but a tapestry of clusters, filaments, and immense voids, with the Butter's void standing as one of the most dramatic examples of emptiness. The discovery of the Butter's void also inspired new generations of astronomers and cosmologists to probe the universe with ever greater precision. It highlighted the importance of surveying vast regions of the sky, not merely focusing on individual galaxies or clusters. Wide-field surveys, combined with spectroscopic measurements, became essential tools in mapping the cosmic web, uncovering the intricate balance between matter and emptiness that shapes the large-scale structure of the universe. The Butter's void, with its nearly 250 million light-year diameter, served as a reminder that the universe operates on scales far beyond human experience, and that even the emptiest regions can hold profound significance for our understanding of cosmic evolution. In addition, the discovery helped refine theories of cosmic evolution. The existence of such a void suggested that gravitational processes, combined with the expansion of the universe, could lead to the evacuation of matter from enormous regions, pushing galaxies into walls and filaments that outline the voids. This insight connected observational astronomy with theoretical models, illustrating how careful measurement and mapping could inform a deeper understanding of the universe's history. It became clear that voids were not mere absences but dynamic regions shaped by the same forces that create clusters and superclusters, reflecting the interplay of gravity, expansion, and the primordial seeds of structure. Even decades later, the Butter's void remains a subject of fascination. Its discovery in the early 1980s marked a turning point in how astronomers perceive the cosmos, shifting the focus from individual galaxies to the grand architecture of the universe itself. The methods developed and refined during its identification, the painstaking redshift surveys, the careful mapping, and the rigorous verification of data, set a standard for astronomical research. These techniques laid the groundwork for later surveys that would map millions of galaxies, revealing an even more intricate cosmic web and placing the Butter's void within a broader context of voids, filaments, and superclusters. The discovery of the Butter's void is a story of human curiosity and perseverance, of astronomers peering into the night sky and seeing patterns that at first seemed impossible. It is a tale of the methods and ingenuity required to detect emptiness on a scale so vast that it stretches the imagination, of the careful observations and calculations that transformed a region of the sky into one of the most famous voids in the cosmos. It reminds us that even in a universe dominated by matter, the empty spaces, those vast regions where galaxies are few and far between, hold crucial clues about the nature of cosmic evolution, the forces that shape the universe, and the very fabric of space and time. Understanding the size and scale of the Butter's void is not merely a matter of curiosity. It is central to our understanding of the universe's structure, the forces that shape it, and the mysterious processes that govern the distribution of the matter on the larger scales. When contemplating the Butter's void, one must grapple with dimensions that are so enormous that they challenge the limits of human comprehension, stretching the imagination far beyond the scale of even our most familiar cosmic structures. At its heart, the Butter's void is a vast spherical expanse nearly devoid of galaxies. To truly appreciate its enormity, one must begin by considering the size of the typical galaxy. Our own galaxy, the Milky Way, has a diameter of roughly 100,000 light-years, a distance so immense that light itself, travelling at nearly 300,000 kilometers per second, requires 100,000 years to traverse it from one edge to the other. And yet, when placed within the Butter's void, even a galaxy as grand as the Milky Way seems almost inconsequential. The Butter's void spans approximately 300 million light-years across, which is 3,000 times the diameter of the Milky Way. This means that if one could place a galaxy like the Milky Way at the centre of the Butter's void, there would still be an empty region extending 1,500 Milky Ways in every direction before encountering another significant galaxy cluster. The scale is so enormous that conventional analogies begin to fail, We are dealing with distances and volumes that defy everyday experience, entering a realm where emptiness itself becomes a dominant feature of the universe. The concept of a galaxy cluster provides another layer of context for understanding the Bhuta's void's magnitude. Galaxy clusters are collections of hundreds or even thousands of galaxies bound together by gravity. Some of the most massive known clusters, such as the Coma cluster or the Virgo cluster, span a few million light-years across. While these clusters contain vast numbers of galaxies, the Bhuta's void is nearly empty by comparison. The size of the void is roughly 100 times the diameter of a typical galaxy cluster. To imagine this, one could picture an enormous cosmic desert stretching in all directions, a region so sparse that the usual markers of galactic civilization, spiral arms, glowing nebulae, and radiant galactic cores, are almost entirely absent. Even the occasional galaxy that exists within the Bhuta's void is usually solitary and isolated, like a lone tree in a vast empty desert. To place the Bhuta's void in an even broader cosmological context, one must consider the scale of the observable universe itself. The observable universe extends approximately 93 billion light-years in diameter, a distance that encompasses all matter and energy from which light has had time to reach Earth since the universe began nearly 13 billion and 800 million years ago. In comparison, the Bhuta's void occupies a fraction of a percent of this observable volume, yet its relative emptiness makes it stand out like a colossal bubble within the cosmic web. While the universe as a whole is a complex network of filaments, sheets, and voids, the Bhuta's void is one of the largest and most striking examples of a void, making it a significant subject of study for understanding the large-scale structure of the cosmos. Its discovery challenged astronomers to rethink previous assumptions about uniformity and homogeneity on cosmic scales, prompting new theories about how matter congregates and how gravity sculpts the universe. The methods by which astronomers have measured and understood the size of the Bhuta's void are themselves fascinating and deeply scientific. In the early 1980s, large-scale redshift surveys became available, allowing astronomers to map the positions of galaxies in 3 dimensions rather than simply observing them in 2-dimensional projections on the sky. Redshift, which refers to the stretching of light to longer wavelengths as objects move away from us due to the expansion of the universe, provides a cosmic yardstick, enabling scientists to calculate the distance of a galaxy with remarkable precision. By compiling redshifts for thousands of galaxies, researchers could identify regions where galaxies were conspicuously absent. The Bhuta's void emerged clearly in these surveys as a nearly spherical region, extending roughly 300 million light-years across, devoid of the dense clustering that characterizes much of the universe. It was an observation that seemed almost paradoxical. How could such a vast empty space exist in a universe that, on smaller scales, appears so full and teeming with structure? One of the most intriguing aspects of the Bhuta's void is the contrast it provides with the cosmic web, the vast, intricate network of filaments and nodes formed by galaxies and dark matter. The cosmic web is a manifestation of the gravitational collapse of matter over billions of years, where galaxies and clusters form along filaments that span hundreds of millions of light-years. Between these filaments lie the voids, vast regions of low-density matter, with the Bhuta's void being among the most extreme examples. The void's sheer emptiness suggests that whatever matter once existed in this region either collapsed into distant filaments or was prevented from forming galaxies due to complex interactions with dark energy, cosmic expansion, or other yet undiscovered forces. Its existence challenges astronomers to understand not only the mechanics of galaxy formation, but also the subtle balance between matter, gravity, and the mysterious components of the universe that govern its expansion. Comparing the Bhuta's void to individual galaxies, clusters, and superclusters illuminates the profound scale differences involved. Consider a galaxy like Andromeda, slightly larger than the Milky Way, which is located roughly 2.5 million light-years away from our own galaxy. In the cosmic neighbourhood, that distance seems vast, yet it is minuscule compared to the 300 million light-year diameter of the Bhuta's void. Even massive clusters such as the Virgo supercluster, which contains the Milky Way, the Local Group, and thousands of other galaxies, is dwarfed by the void. The Bhuta's void size exceeds that of typical superclusters, indicating that its emptiness is not merely a statistical fluctuation, but a genuine, significant feature of the universe's structure. It is as if one could remove an entire neighbourhood of superclusters and still have room for hundreds more within the void's vast expanse. Another way to grasp its scale is through volume. The volume of a sphere grows with the cube of its radius, which means that a void 300 million light-years across encompasses an incomprehensible volume of roughly 14 million cubic megaparsecs, or in more familiar terms, a number of cubic light-years that reaches beyond easy calculation. Which means that a void 300 million light-years across encompasses an incomprehensible volume of roughly 14 million cubic megaparsecs, or in more familiar terms, a number of cubic light-years that reaches beyond easy calculation. Within this space, the density of galaxies is drastically lower than the average cosmic density, often less than 1% of what is typical in the universe. Even with occasional galaxies scattered within the void, they are isolated and removed from the cosmic filaments that otherwise dominate the universe. To put this into perspective, the Butter's void is to a galaxy cluster what a single cubic meter of air is to the Earth's atmosphere. A vast, empty space where the usual occupants are nearly entirely absent. The scientific implications of the Butter's void extend beyond simple size comparisons. Its existence provides critical insights into cosmology, particularly in the study of dark matter, dark energy, and the formation of large-scale structures. The standard cosmological model predicts a distribution of matter that is lumpy, with dense regions and vast voids. But the Butter's void tests the extremes of these predictions. Studying its boundaries and the few galaxies that inhabit it allows scientists to trace the forces that shape cosmic evolution. For example, galaxies near the edges of the void tend to be oriented along the filaments that bound it, hinting at the gravitational interactions that sculpt the void's shape. In essence, the Butter's void is not just empty space. It is a laboratory where the interplay of gravity, cosmic expansion, and matter distribution can be studied on the grandest of scales. Cosmic voids are among the most fascinating and mysterious features of our universe, yet they are often less understood than the bright stars, galaxies, and clusters that dominate our night sky. These enormous regions of space are, in essence, vast expanses where very few galaxies exist, a kind of cosmic emptiness that stretches across millions of light-years. Despite appearing empty at first glance, cosmic voids are crucial to our understanding of how the universe came to look the way it does today. They are not merely holes in space. They are dynamic structures that tell a story about the universe's origin, evolution, and the underlying physics that govern everything from the tiniest particle to the largest cosmic structures. To begin with, the concept of a cosmic void requires understanding what the universe looks like on its larger scales. When astronomers observe the universe, they do not see a uniform distribution of galaxies. Instead, galaxies form a web-like pattern called the cosmic web, where dense clusters of galaxies are connected by filaments and sheets of matter, and between these structures lie enormous regions of relatively empty space, the voids. These voids can range from tens of millions to over 100 million light-years across. To put this in perspective, 1 light-year is the distance that light travels in 1 year, which is roughly 6 trillion miles. Therefore, a void that is 100 million light-years across is a region so immense that even light would take 100 million years to cross it. This immense scale alone is difficult for the human mind to truly grasp, yet it is a fundamental part of the cosmic landscape. Cosmic voids are not entirely empty. They contain small numbers of galaxies, sparse clouds of gas, and dark matter, which is an invisible form of matter that does not emit or absorb light but exerts gravitational influence on visible matter. The density of these regions is far lower than that of the cosmic filaments or clusters, sometimes less than 1/10 of the average density of the universe. Despite their low density, voids are still dynamic and active regions. Galaxies within them are often smaller, less massive, and less likely to form new stars than those in denser regions. The gas in voids is thinner and cooler, and the gravitational pull is weaker, which affects how structures evolve over time. Understanding how voids form requires a look back in time to the very early universe, shortly after the Big Bang, which occurred approximately 13,800 million years ago. The early universe was almost, but not perfectly, uniform. Tiny fluctuations in density existed, with some regions slightly denser and others slightly less dense. These fluctuations were incredibly small, only a few parts in 100,000, yet they set the stage for all the structure we see today. Over time, gravity acted on these differences. Denser regions attracted more matter, becoming even denser, eventually forming the stars, galaxies, and clusters we see today. Conversely, less dense regions had weaker gravitational attraction, so matter flowed away from them toward denser areas. As a result, these underdense regions grew emptier over billions of years, forming the cosmic voids we observe in the present-day universe. In essence, voids are the leftover spaces created by the gravitational sculpting of matter into filaments and clusters. The process of void formation is also influenced by the expansion of the universe. The universe has been expanding since the Big Bang, a fact first observed by Edwin Hubble in 1929 when he discovered that galaxies were moving away from us, with more distant galaxies moving faster. This expansion stretches space itself, and in underdense regions the effect is even more pronounced because there is less gravitational pull to slow it down. As a result, voids expand faster than denser regions, and their boundaries, where the sparse interior meets denser filaments, become more distinct over time. This is why voids can reach such enormous sizes, sometimes rivaling the size of superclusters of galaxies. Voids are not perfectly spherical, although early models often treated them as idealized spheres for simplicity. In reality, they are irregularly shaped, sometimes elongated or flattened, reflecting the complex distribution of matter around them. Their shapes provide valuable information about the distribution of dark matter and the overall geometry of the universe. By studying voids, astronomers can test cosmological models and gain insights into dark energy, the mysterious force that drives the accelerated expansion of the universe. Some of the largest known voids, like the Booter's Void discovered in 1981, are nearly 100 million light-years across, containing only a few dozen galaxies in a region where tens of thousands might be expected based on average cosmic density. These immense voids serve as natural laboratories for studying how galaxies evolve in isolation and how large-scale cosmic structures develop over time. The study of voids also helps astronomers understand the distribution of dark matter. While dark matter cannot be seen directly, its gravitational influence shapes the cosmic web, including the formation and growth of voids. In simulations of the universe, regions with less dark matter become underdense, naturally forming voids as visible matter is pulled toward areas of higher density. This relationship between voids and dark matter provides a unique opportunity to study the invisible scaffolding of the cosmos, as the patterns and shapes of voids reflect the underlying dark matter distribution. Another important aspect of voids is their effect on the cosmic microwave background radiation, which is the afterglow of the Big Bang. As light from this radiation passes through voids, it experiences a slight change in energy due to the gravitational influence of the underdense regions, a phenomenon known as the integrated Sachs-Wolf effect. By measuring these tiny changes, astronomers can learn about the expansion history of the universe and the properties of dark energy. Voids, therefore, are not empty or irrelevant. They are active participants in the cosmic story, influencing the motion of galaxies, the propagation of light, and the evolution of cosmic structures. Void galaxies, the few galaxies that inhabit these vast empty regions, also offer intriguing insights. Because they are relatively isolated, they are less affected by the interactions and mergers that drive the evolution of galaxies in denser regions. Many of these galaxies are small, faint, and rich in gas, making them ideal laboratories for studying star formation in a pristine environment. Observations show that some void galaxies have unusual properties, such as low metallicity, meaning they contain fewer heavy elements, which suggests they have evolved more slowly than galaxies in crowded regions. By examining these cosmic outliers, astronomers can gain a deeper understanding of how the environment influences galaxy formation and evolution. The existence of voids also challenges and refines theoretical models of the universe. When large surveys of galaxies, such as the Sloan Digital Sky Survey, mapped the three-dimensional distribution of galaxies across millions of light-years, the intricate pattern of filaments and voids became apparent. These maps confirmed predictions from the theory of cosmic inflation, which posits that the universe underwent an extremely rapid expansion in its first fraction of a second. Inflation would have smoothed out the universe while leaving tiny quantum fluctuations, which eventually grew into the density variations responsible for both galaxies and voids. Therefore, voids are not random. They are the natural outcome of the physical processes that shape the universe on the larger scales. Voids also exhibit hierarchical structures. Within large voids, smaller voids can exist, creating a nested pattern sometimes described as a void hierarchy. Smaller voids expand and merge over time, similar to bubbles in a foam. This hierarchical behavior reflects the way gravity acts differently on various scales, producing a cosmic structure that is both simple in its basic principles and complex in its detailed patterns. Studying these hierarchies allows astronomers to better understand the interplay between gravity, dark matter, and the expansion of the universe. Another fascinating feature of voids is their low-velocity dispersion. In denser regions, galaxies move rapidly due to the strong gravitational pull of nearby structures. In contrast, galaxies in voids move more slowly relative to the cosmic expansion, as they are less influenced by surrounding mass. This slow motion allows astronomers to trace the history of void expansion and to measure cosmological parameters, such as the Hubble constant, in unique ways. Observations of galaxy motion within voids complement studies in denser regions, providing a more complete picture of cosmic dynamics. Cosmic voids also have implications for understanding the future evolution of the universe. As the universe continues to expand, voids are expected to grow even larger, gradually dominating the volume of space. Some models suggest that in the far future, most galaxies will be found in isolated clusters surrounded by vast empty voids, with the filaments and smaller structures becoming less connected. Studying current voids, therefore, offers a glimpse into the long-term fate of the cosmos and helps astronomers predict how structures will evolve over tens of billions of years. It is also worth noting that voids have inspired philosophical and cultural reflection. Their vast emptiness challenges our perception of the universe as a place filled with stars and galaxies. Instead, they remind us that the universe is a delicate balance between presence and absence, structure and emptiness, matter and space. The study of voids, therefore, is not only a scientific endeavour, but also an exploration of our place in a cosmos that is both immense and sparsely populated on the larger scales. The study of cosmic voids continues to advance rapidly. New surveys and powerful telescopes, both on Earth and in space, are mapping the universe in ever greater detail. Each new observation adds to our understanding of these vast emptinesses, revealing subtle patterns and structures that challenge our theories and stimulate new ideas. As we peer deeper into the cosmos, voids remind us that even in the emptiest regions, there is a wealth of knowledge waiting to be discovered, a silent yet profound testament to the universe's vast and intricate design. Cosmic voids, in their immense scale, in their quiet expanses, and in their mysterious contents, remain among the most compelling subjects in modern astrophysics. They embody the paradox of emptiness that is full of information, a paradox that drives astronomers to continue exploring, questioning, and uncovering the secrets of the universe, one void at a time. To understand its structure, and to appreciate the methods astronomers use to map it, we must begin by thinking of the universe not as a uniform, evenly filled space, but as a vast cosmic web, a complex tapestry of matter and emptiness, of galaxies and gaping voids. The universe is not a smooth soup of stars and galaxies. Instead, matter collects along enormous filaments and sheets, forming intricate networks that intersect at nodes, where clusters of galaxies gather in dense knots, leaving enormous regions between them that are comparatively empty. These empty regions are what astronomers call cosmic voids, and among them, the Butter's void stands as one of the largest and most fascinating examples ever discovered. The Butter's void, first identified in 1987 by a team led by astronomer Robert Kirshner, is a truly astonishing expanse. It is roughly 600 million light-years across, a number so vast that it is almost impossible to truly visualize. To put it into perspective, the Milky Way, our galaxy, is a mere 100,000 light-years across. That means the Butter's void is approximately 6,000 times wider than the Milky Way. Some estimates even suggest that it contains only about 60 galaxies, which is an incredibly tiny number given its immense size. In comparison, our local neighbourhood alone, the Virgo supercluster, contains thousands of galaxies. The emptiness of the Butter's void is so profound that when astronomers look into it, the light of galaxies is scarce, making it appear as a nearly black yawning chasm in the otherwise luminous fabric of the cosmos. Mapping the Buta's void was not a simple task. Astronomers rely on detailed surveys of galaxies and their positions in space to trace the large-scale structure of the universe. One of the key methods used is redshift mapping, which measures how much the light from distant galaxies has been stretched due to the expansion of the universe. The greater the redshift, the farther away the galaxy is, and by combining the positions of galaxies across the sky with their redshift distances, astronomers can construct a three-dimensional map of the universe. In the case of the Buta's void, astronomers meticulously plotted the locations of galaxies within a vast volume of space in the Buta's constellation, noting the gaps and areas where galaxies were nearly absent. This painstaking work revealed a colossal, roughly spherical region that was strikingly devoid of galaxies, a true void in the cosmic web. Interestingly, the Buta's void is not entirely empty. Although it is overwhelmingly sparse, astronomers have detected a small number of galaxies scattered throughout it. These galaxies are often isolated, living in solitary conditions far from the dense clusters and filaments that dominate other regions of space. Their isolation offers astronomers a unique laboratory for studying galaxy formation in extreme conditions. Unlike galaxies in crowded regions, which interact frequently with neighbouring galaxies, the galaxies in the Buta's void evolve with minimal external influence. This allows scientists to observe how galaxies grow and change in isolation, revealing clues about the fundamental processes that shape galactic structures over billions of years. The patterns of matter within the Buta's void are equally fascinating. While it is mostly empty, the void is not a perfect vacuum. It contains traces of dark matter, the invisible substance that exerts gravitational influence on the universe but does not emit light. Dark matter forms the scaffolding of the cosmos, guiding the formation of galaxies and the structure of filaments and voids. Even within the Buta's void, the gravitational presence of dark matter subtly influences the motions of the few galaxies that exist there. This faint web of dark matter suggests that the void, while almost devoid of luminous matter, is still part of the grand cosmic structure, connected to the surrounding filaments and clusters through gravitational threads that stretch across the emptiness. To better understand the void structure, astronomers also use simulations of the universe. These computer-generated models recreate the evolution of matter from the early universe, just after the Big Bang, to the present day. By comparing these simulations with observations, scientists can see how voids like the Buta's void naturally form. The simulations show that as matter clumps together under gravity, regions of higher density pull in surrounding material, leaving behind areas of lower density. Over billions of years, these underdense regions expand, merging with neighbouring voids to create enormous empty spaces. The Buta's void likely formed through this process, a combination of gravitational attraction and cosmic expansion sculpting the vast emptiness we observe today. Another intriguing aspect of the Buta's void is its shape. While it is often described as roughly spherical, careful mapping reveals that it is not a perfect sphere. It has irregularities, slight elongations, and variations in density. Some regions within the void are slightly denser than others, containing small filaments of matter or isolated galaxies. This uneven distribution hints at the dynamic nature of the void's formation. It is not a static, empty bubble, but a region that has evolved over billions of years, influenced by the surrounding cosmic structures and the complex interplay of gravity, dark matter, and the expansion of space itself. The Buta's void also challenges our understanding of cosmic evolution. Its sheer size and emptiness raise questions about how such a massive void could form without significant amounts of matter. Some theories suggest that it may have formed from the merging of smaller voids, each initially sparse, which over time coalesced into one gigantic region of emptiness. Others propose that rare fluctuations in the density of matter in the early universe could have led to the creation of such a vast void. While the exact details remain uncertain, the Buta's void stands as a reminder that the universe is full of extremes, regions of astonishing density and nearly unimaginable emptiness, all woven together in a delicate cosmic tapestry. Astronomers continue to study the Buta's void using increasingly sophisticated tools. Modern telescopes, both ground-based and spaceborne, allow scientists to peer deeper into the void, detecting faint galaxies and measuring their properties. Surveys like the Sloan Digital Sky Survey have provided detailed maps of millions of galaxies, giving a clearer picture of the void's boundaries and internal structure. By analysing the light from these distant galaxies, astronomers can measure their chemical compositions, star formation rates, and motions, building a detailed understanding of life inside this lonely region of space. These studies reveal that even in such a seemingly empty region, the few galaxies that exist can tell us much about the processes that govern the cosmos. The study of the Bhuta's void also has broader implications for cosmology, the study of the universe as a whole. Voids are sensitive to the properties of dark energy, the mysterious force driving the accelerated expansion of the universe. Because voids expand faster than regions of higher density, their growth patterns can provide clues about the nature of dark energy. By carefully measuring the size, shape, and expansion of the Bhuta's void and other cosmic voids, scientists hope to test models of dark energy and gain insight into one of the greatest mysteries of modern physics. In this way, the Bhuta's void is not just an empty space, it is a cosmic laboratory, offering a unique window into the fundamental forces shaping the universe. Another fascinating aspect of the Bhuta's void is the role of cosmic filaments surrounding it. Filaments are enormous, thread-like structures of galaxies and dark matter that connect clusters across vast distances. Around the void, these filaments form a skeleton, outlining its boundaries and influencing the motion of galaxies at its edges. Galaxies at the edge of the Bhuta's void experience gravitational pull from these filaments, which can sometimes lead to peculiar motions or even trigger bursts of star formation. Studying these interactions helps astronomers understand how voids and filaments coexist in the cosmic web, and how the large-scale distribution of matter influences the evolution of galaxies in different environments. Interestingly, the Bhuta's void also has cultural and scientific significance beyond its physical properties. When it was first discovered, it captured the imagination of the scientific community and the public alike. Its enormous size and the eerie emptiness within it inspired comparisons to deserts and other vast, lonely landscapes, prompting discussions about the nature of nothingness on a cosmic scale. The void became a symbol of the universe's extremes, illustrating that space is not uniform, and that the cosmos can contain regions almost entirely devoid of matter. It serves as a reminder that, even in a universe filled with countless stars and galaxies, emptiness is just as fundamental a feature as the matter that forms the familiar objects we see in the night sky. Mapping the Bhuta's void required extraordinary precision and collaboration. Teams of astronomers around the world pulled data from multiple surveys, carefully cross-checking observations to ensure that what appeared to be empty space was truly devoid of galaxies and not simply a result of observational limitations. This work involved not only measuring the positions of galaxies, but also correcting for effects such as cosmic dust, which can obscure distant light, and gravitational lensing, which can distort the apparent positions of galaxies. The resulting maps are among the most detailed representations of large-scale cosmic voids ever created, showing the Bhuta's void as a nearly spherical region, with a few isolated galaxies sprinkled within, surrounded by a dense network of filaments and clusters that define the cosmic web. The few galaxies that do exist inside the Bhuta's void are intriguing in themselves. They tend to be smaller, less massive, and less luminous than typical galaxies in denser regions. Some are irregular in shape, lacking the clear spiral or elliptical forms that dominate more populated areas of the universe. Their isolation allows astronomers to study galactic evolution in a nearly pristine environment, free from the gravitational interactions and mergers that shape galaxies and clusters. Observing these galaxies provides insight into how stars form, how gas flows within galaxies, and how galaxies grow in the absence of external influence. These isolated galaxies are silent witnesses to billions of years of cosmic history, living in solitude in one of the largest empty regions of the universe. Despite its emptiness, the Bhuta's void is an essential component of the universe's structure. Its size and presence affect the motion of surrounding galaxies, influencing the expansion of nearby filaments and clusters. The void acts like a gravitational bubble, pushing matter outward as the universe expands, contributing to the overall large-scale pattern of motion in the cosmos. Studying these motions helps astronomers understand not only the distribution of visible matter, but also the influence of dark matter and dark energy, which together make up the vast majority of the universe. In this sense, the Bhuta's void is far from meaningless emptiness. It plays an active role in shaping the cosmic landscape, demonstrating that even regions with very little matter can have profound effects on the universe as a whole. The discovery of galaxies inside the Booter's Void was one of those moments in astronomy that completely changed how scientists thought about the universe. For a long time, when astronomers first found this enormous cosmic emptiness, they called it a void because it seemed to be utterly empty, a place where galaxies were almost entirely absent. This immense region of space, stretching over 300 million light-years across, was not merely a sparse region of stars and galaxies. It appeared at first to be a vast desert in the cosmic landscape. To early observers, the idea that such a gigantic void could exist without a single galaxy seemed almost impossible. After all, the universe is overwhelmingly made of galaxies, galaxy clusters, and filaments of matter. So to find a place that seemed completely devoid of them was like stumbling upon a desert in the middle of a bustling city, a place you could hardly believe could exist. Yet as astronomers continued to observe the Booter's Void with more sensitive instruments and more careful surveys, a remarkable truth began to emerge. The void was not entirely empty. Small, isolated galaxies were scattered within its vast expanse, hiding in plain sight, waiting for the telescopes to catch them. These discoveries were surprising, because the void is enormous, with a diameter of roughly 300 million light-years, making it one of the largest known empty regions in the universe. To put this in perspective, a typical galaxy such as our Milky Way might have only a few thousand or tens of thousands of light-years across. So, the Booter's Void is almost 10,000 times larger in diameter than an ordinary galaxy, and yet, even within such a massive emptiness, galaxies managed to survive and form. The first hints that the Booter's Void contained galaxies came from deep surveys that carefully mapped the distribution of galaxies across the sky. Using these surveys, astronomers began to detect faint points of light where no galaxies had been expected. At first, these detections were puzzling. Scientists wondered if the signals were errors, perhaps caused by the limits of their instruments or by cosmic dust that interfered with observations. However, repeated measurements confirmed that these points of light were indeed galaxies. Slowly the void revealed its hidden structure, showing that even the most seemingly empty regions of space contain matter, even if only sparsely scattered. One of the most surprising aspects of these galaxies inside the Booter's Void is their isolation. Unlike galaxies in clusters, where hundreds or even thousands of galaxies can be found in close proximity, these void galaxies are often millions of light-years away from their nearest neighbours. This means they live in an extremely low-density environment, where gravitational interactions with other galaxies are rare. In such isolation, these galaxies evolve very differently from those in crowded regions. They often appear smaller, fainter, and sometimes irregular in shape, as though their development has been shaped more by solitude than by interaction. In some cases, they have managed to retain vast amounts of gas, which in more crowded regions might have been stripped away by the gravitational pull of nearby galaxies. This abundance of gas allows them to form stars over longer periods, giving them a slow, steady pace of evolution. The discovery of these isolated galaxies inside the void also raised profound questions about how galaxies form in the first place. If galaxies need dense regions of matter to clump together, then why are there galaxies in such an extremely low-density environment? The answer lies in the nature of the universe's large-scale structure. Even in the emptiest regions, there are subtle threads of matter, invisible filaments that stretch across space, connecting one area to another. These filaments provide the seeds from which galaxies can form, even in places that appear empty. The galaxies inside the Booter's Void seem to have formed along these faint filaments, surviving in isolation while the rest of the void remains mostly empty. Observing these galaxies is no simple task, because they are few and far between and often faint. They require powerful telescopes and sensitive instruments to detect. Astronomers have used both ground-based telescopes and space observatories to study them. Over the years, surveys such as the Sloan Digital Sky Survey, which began in 1998, have mapped large portions of the sky with unprecedented detail, revealing hundreds of previously hidden galaxies within the Booter's Void and other similar cosmic voids. Each new detection adds to our understanding of the void's structure, showing that even these enormous empty regions are not completely barren, but are instead punctuated by small oases of matter. tiny islands of galaxies in a cosmic desert. The nature of these galaxies inside the void is also fascinating from a chemical and stellar perspective. Because they are isolated and evolve slowly, many void galaxies have retained their original gas compositions to a greater extent than galaxies in denser regions. This allows astronomers to study them as relatively pristine examples of galaxy evolution. Some of them have very few heavy elements, meaning they resemble the early galaxies of the universe, whose stars formed when the cosmos was still young. In this way, the Bhuta's void becomes not just a curiosity, but a laboratory for understanding galaxy formation, chemical evolution, and the history of the universe itself. Another intriguing aspect of void galaxies is their distribution. While the Bhuta's void is mostly empty, the galaxies that do exist are not entirely random in their placement. They tend to trace faint, almost invisible filaments of dark matter, the mysterious substance that permeates the universe and shapes its large-scale structure. These filaments act as cosmic scaffolding, guiding where galaxies can form and survive. The fact that even in the emptiest regions of the universe, galaxies are not randomly scattered, but instead follow these underlying structures, reveals the deep and subtle order of the cosmos. The discovery of galaxies inside the Bhuta's void also carries implications for our understanding of the universe as a whole. It shows that emptiness in space is not absolute. Even in regions that appear devoid of matter, small pockets of activity, islands of matter, and galaxies persist. This challenges simplistic notions of cosmic emptiness and demonstrates that the universe's structure is far more intricate and interconnected than once imagined. The voids are not merely gaps between clusters and filaments, they are active regions in their own right, harbouring unique galaxies that tell us about the universe's history, composition, and evolution. In addition, these discoveries have prompted astronomers to look for void galaxies in other regions of space. Surveys of the nearby universe have revealed similar isolated galaxies in voids throughout the cosmos, confirming that what is seen in the Bhuta's void is not an anomaly, but part of a larger pattern. The universe, it seems, is a vast tapestry of matter and emptiness, where even the emptiest regions hold tiny, remarkable structures that have persisted over billions of years. Studying these galaxies also helps astronomers refine their models of cosmic evolution. Theories of galaxy formation must now account for the existence of isolated galaxies in extreme environments where gravitational interactions are minimal. This has led to improved simulations of cosmic evolution, showing how galaxies can form and survive in both crowded and empty regions, influenced by the subtle scaffolding of dark matter and the leftover gas from the early universe. The human fascination with the idea of emptiness in space takes on a new dimension with the discovery of these galaxies. What once seemed like a vast void, a nothingness stretching for hundreds of millions of light years, is now understood to contain hidden islands of light, tiny galaxies that persist despite extreme isolation. This transforms our understanding of voids from being absolute emptiness to being sparse but structured regions, a subtle network of matter punctuating a seemingly barren expanse. Astronomers continue to explore the Bhuta's void, and each new galaxy discovered inside it adds to our understanding of the universe's large-scale structure. The void's galaxies challenge our expectations, showing that even in the largest gaps between clusters and superclusters, the universe's creativity continues. They serve as reminders that space is never truly empty, that even in the quietest corners of the cosmos, galaxies can form, evolve, and survive for billions of years. The discovery of galaxies inside the Bhuta's void ultimately highlights the universe's complexity and subtlety. It shows that emptiness is relative, that the largest voids can contain small but significant structures, and that our understanding of the cosmos is always evolving. Even in a region that stretches over 300 million light-years, which initially seemed devoid of galaxies, we find life in the form of tiny, isolated galaxies, quietly moving through the darkness, slowly forming stars, and tracing the invisible threads of matter that bind the universe together. These galaxies also offer a unique perspective on cosmic time. Because they evolve more slowly, and because their environment is so different from galaxies and clusters, they preserve a kind of memory of the early universe. Observing them allows scientists to peer back in time, to understand how galaxies might have looked when the universe was only a fraction of its current age. In this sense, the Bhuta's void is not just a space of emptiness, but a cosmic archive, preserving clues about the formation and evolution of galaxies over billions of years. Furthermore, the study of void galaxies emphasizes the importance of careful observation and technological advancement in astronomy. Without sensitive instruments capable of detecting faint light from distant galaxies, these isolated galaxies would remain hidden, and the Boötes void would continue to be seen as truly empty. The discoveries remind us that the universe often contains surprises, and that the limits of our perception can obscure the richness of cosmic structures. In the vastness of the universe, galaxies are rarely completely alone. Most are part of an immense cosmic web, a grand tapestry woven from threads of dark matter, gas, and galaxies themselves. In this web, galaxies interact, collide, and merge, exchanging gas and dust, sparking waves of star formation, and sometimes triggering spectacular bursts of activity around their central black holes. The universe, in this sense, is more like a bustling city than a quiet countryside, full of neighborhoods where galaxies gather in clusters and groups, constantly influencing one another. Yet, amid this crowded cosmos, there are regions that seem almost eerily empty, places so vast and lonely that they appear to float in a silent cosmic ocean. These regions are known as cosmic voids, and within them lie the most isolated galaxies in the universe, galaxies living in profound solitude, cut off from the frenetic activity of the cosmic web. To understand the life of a galaxy in isolation, we must first grasp the scale and emptiness of the spaces they inhabit. Cosmic voids are enormous. They stretch across tens to hundreds of millions of light years, spanning distances that defy human imagination. Within such voids, the density of matter, both visible and invisible, is remarkably low. While typical regions of the universe teem with galaxies, these voids may contain only a few scattered galaxies, sometimes no more than one galaxy for every 10 million cubic light years. Imagine, if you can, being in a city with neighborhoods filled with countless people, and then stepping into an empty countryside so vast that a single individual seems almost like an intruder in a desert. This is what void galaxies experience on a cosmic scale, an existence defined by extreme isolation. Isolation affects galaxies in profound ways. Galaxies in dense regions of the cosmic web often experience gravitational tugs from their neighbours, sometimes pulling them closer until they merge, or triggering shocks in their gas that ignite waves of star formation. But a void galaxy, alone in its silent territory, is largely immune to these external influences. It does not collide with other galaxies frequently, nor does it experience the constant tidal forces that shape galaxies and clusters. Its evolution is driven almost entirely by internal processes. In a sense, a void galaxy is left to its own devices, forced to evolve slowly, quietly, and independently. While galaxies in crowded clusters may burn brightly and rapidly, consuming their gas in a flurry of star formation, a void galaxy often grows at a languid pace. Its stars form more slowly, its gas is less likely to be stripped away by interactions, and its life cycle stretches over billions of years in a more measured rhythm. The isolation of void galaxies also affects their structure and appearance. Many isolated galaxies are smaller, less massive, and more irregular in shape compared to their cluster-dwelling cousins. They often retain higher proportions of gas relative to their stars, giving them the potential to continue forming new stars for long periods. In contrast, galaxies and clusters frequently lose their gas due to interactions, halting star formation, and leaving behind older, redder stars. Observations have shown that void galaxies are often bluer, signalling ongoing star formation, albeit at a leisurely pace. Their spiral arms may be less tightly wound, and their shapes can be more chaotic, reflecting the absence of external gravitational pressures that would otherwise mold them into more orderly forms. In many ways, these galaxies are like cosmic adolescents, developing and changing slowly, shielded from the stresses of a crowded environment. Yet, isolation does not mean emptiness. Even in the deepest voids, galaxies can have companions, though they are few and far between. Some voids contain small, loose groups of galaxies, wandering together through the vast expanse. But even these groups are exceedingly sparse compared to the dense clusters found in the cosmic web. When void galaxies do interact, the encounters are rare and gentle, often insufficient to trigger the dramatic transformations seen in denser regions. Instead, these galaxies maintain their individuality, growing and evolving without being shaped or dominated by neighbours. They provide a unique laboratory for astronomers, allowing scientists to study how galaxies evolve under conditions of extreme isolation, untouched by the usual environmental pressures. The study of void galaxies also sheds light on the fundamental nature of the universe itself. Cosmologists have long known that matter in the universe is distributed unevenly. While clusters, filaments, and walls of galaxies form a complex and interconnected web, the voids are the large gaps in between. By observing the properties of galaxies in these empty regions, astronomers can test theories of galaxy formation and cosmic evolution in environments far removed from the gravitational influences and energetic interactions that dominate denser regions. For instance, by comparing the star formation rates, gas content, and chemical compositions of void galaxies with those of galaxies and clusters, scientists can identify which characteristics of galaxies are driven by nature, their internal processes, and which are shaped by nurture, the influence of environment. Void galaxies in this sense serve as a window into the most basic, unperturbed processes of cosmic evolution, offering insights that cannot be gleaned from studying galaxies in crowded cosmic neighbourhoods. Interestingly, despite their isolation, void galaxies are not entirely immune to the broader currents of the universe. Large-scale motions of matter driven by the gravitational pull of massive structures far away can subtly influence even these distant galaxies. Over billions of years, void galaxies may drift slowly toward denser filaments or clusters, eventually leaving the voids behind. Some may even experience interactions with the few neighbours scattered within the void, though such events are rare. Nonetheless, the vast majority of their existence is spent in solitude, evolving in a universe that seems to move around them, while they remain comparatively undisturbed in their silent cosmic homes. Astronomers have catalogued many void galaxies, thanks to detailed surveys of the sky conducted over the past several decades. One of the most notable regions studied is the Bhuta's Void, first identified in the 1980s, a vast emptiness stretching roughly 600 million light-years across. Within this immense void, astronomers have discovered galaxies sparsely scattered throughout, providing concrete examples of cosmic isolation. Observations using advanced telescopes, both ground-based and spaceborne, have revealed that these galaxies are typically smaller and bluer than those in denser regions, confirming that their evolution proceeds at a more leisurely pace. Yet, even in this extreme emptiness, the galaxies are not completely devoid of structure. They often follow faint filamentary patterns, hinting at the subtle influence of the underlying distribution of dark matter, which guides the formation and evolution of all galaxies, even those in the deepest voids. The chemical makeup of void galaxies also reflects their isolation. Because these galaxies interact less frequently, they retain more pristine reservoirs of gas, relatively untouched by the inflow of metals and heavier elements from neighbouring galaxies. This can result in lower metallicity, meaning that the proportion of elements heavier than hydrogen and helium is smaller than in galaxies residing in clusters. Such conditions resemble those of the early universe, providing astronomers with natural laboratories to study processes similar to those that occurred in the cosmos billions of years ago, when galaxies were just beginning to form their first stars. Void galaxies, in a sense, preserve a memory of a simpler cosmic past, offering a glimpse into the unhurried evolution of matter and energy in the universe. Despite their isolation, void galaxies are not necessarily quiet. Internally, they can host dynamic processes such as bursts of star formation triggered by internal instabilities, the collapse of gas clouds under their own gravity, or even the activity of central supermassive black holes, if they have one. However, these activities are generally less intense than those in galaxies that have been disturbed or fueled by interactions with neighbours. Star formation in void galaxies often proceeds in small localized regions rather than in galaxy-wide fireworks. Supernovae, the explosive deaths of massive stars, still occur, enriching their immediate surroundings with heavier elements, but the overall pace of chemical evolution is slower. These galaxies live in a measured rhythm, where change is slow, deliberate, and often subtle, in stark contrast to the turbulent competitive life of galaxies and crowded clusters. The study of void galaxies also challenges our understanding of what it means to be a galaxy. Traditional models of galaxy formation emphasize the role of environment, suggesting that interactions, mergers, and external influences are essential for shaping a galaxy's structure, triggering star formation, and fueling central black holes. Yet void galaxies demonstrate that galaxies can also thrive in isolation, evolving largely on their own. They can develop spiral structures, retain their gas for billions of years, and continue forming stars long after similar galaxies and clusters have exhausted their fuel. They are proof that galaxies are not merely products of their surroundings, but also capable of independent, self-directed evolution. Each void galaxy tells a story of resilience, adaptation, and survival in the face of vast emptiness. Moreover, the existence of void galaxies adds a poetic dimension to our understanding of the universe. In a cosmos dominated by immense structures, filaments, and clusters, these isolated galaxies remind us that solitude can be a defining and meaningful condition. They exist as lonely islands in a sea of emptiness, yet they shine with their own light, forging stars and evolving over billions of years with a quiet dignity. Their isolation, far from being a limitation, allows them to preserve unique characteristics and to act as natural laboratories for scientists seeking to understand the fundamental rules of cosmic evolution. They are witnesses to the silent, unhurried processes that govern the universe on the largest scales, embodying a form of cosmic independence that is as instructive as it is mesmerizing. The vast universe is filled with an astonishing variety of galaxies, each with its own story, each with its own rhythm of growth, change, and light. Among these countless islands of stars, gas, and dust, there exists a rare and remarkable population of galaxies that live in what we call cosmic voids, immense, nearly empty regions of space where the usual bustle of galaxies, clusters, and cosmic filaments is almost entirely absent. These galaxies, known as void galaxies, are cut off from the dense web of matter that threads through the universe, and this isolation profoundly affects the way they live, grow, and shine. One of the most intriguing aspects of void galaxies is the way their solitude influences star formation, a process central to the life of every galaxy. To understand this, we need to explore not just what void galaxies are, but how galaxies form stars in general, how the cosmic environment shapes this process, and what the study of these lonely galaxies tells us about the universe itself. In ordinary cosmic neighborhoods, galaxies are rarely alone. They live in a rich cosmic web composed of filaments, clusters, and sheets of dark matter and gas. Along these filaments, galaxies are relatively close to one another, and their mutual gravitational pulls often trigger interactions and mergers. These encounters stir up gas, compress clouds of hydrogen, and ignite bursts of star formation. In other words, proximity and interaction in the cosmic web can fuel the birth of new stars, sometimes in spectacular starbursts that shine brightly across millions of light years. Galaxies in clusters or along dense filaments have access to fresh supplies of cold gas from the intergalactic medium, which further supports continuous star formation over billions of years. These galaxies are nurtured by their environment. They are fed, shaken, and sometimes even scarred by the cosmic neighborhood they inhabit. Void galaxies, however, are entirely different. They reside in the great cosmic deserts where galaxies are sparse and distances between them are vast. The nearest neighboring galaxy may be tens of millions, or even 100 million light-years away. In such isolation, void galaxies do not experience the frequent gravitational nudges, interactions, or mergers that often stimulate star formation in more crowded regions. Their cosmic diet is limited, and they must rely primarily on the gas they already contain, or can slowly accrete from the sparse void environment. This isolation means that the conditions for forming new stars are often more subdued, slower, and gentler than in typical galaxies. Yet this isolation does not necessarily spell doom for star formation. In fact, astronomers have discovered that void galaxies often have fascinating and surprising characteristics. Many void galaxies are relatively small, often dwarf galaxies with a lower total mass than their more socially connected counterparts. Their modest mass and isolation shield them from disruptive gravitational encounters, which allows their gas to remain stable over long periods. This stability can lead to prolonged, steady star formation, sometimes extending across billions of years. Rather than violent bursts, star formation in void galaxies can be more like a slow, quiet, persistent candle flickering in the darkness. This gentle, enduring process can result in galaxies that appear bluer than expected, as the ongoing creation of young, hot stars gives them a slightly youthful glow compared to older, redder galaxies in denser environments. Another intriguing feature of void galaxies is their gas content. Gas is the essential fuel for star formation, and in more crowded cosmic regions, galaxies can lose much of their gas through tidal interactions, ram pressure stripping, or other environmental effects. Void galaxies, by contrast, are often able to retain a higher proportion of their primordial gas because they are largely free from disruptive external forces. This abundance of gas can be advantageous for star formation, allowing these galaxies to continue producing stars over extended periods, albeit at a typically slower and more measured pace. Observations with powerful radio telescopes have revealed that some void galaxies contain vast reservoirs of neutral hydrogen, sometimes more than similar galaxies and clusters, highlighting how isolation can preserve the raw materials for stellar birth. The type of stars formed in void galaxies can also differ subtly from those in denser regions. Because star formation in void galaxies is less likely to be triggered by dramatic interactions or mergers, the initial mass function, the distribution of star masses, may be skewed towards smaller, longer-lived stars. This can result in a slower enrichment of the galaxy with heavy elements, since massive stars are the primary contributors to the chemical enrichment of the interstellar medium. In essence, void galaxies may evolve chemically at a slower rate, creating a unique environment where both stars and the interstellar medium develop under the gentle influence of isolation rather than the chaotic energy of cosmic crowds. Studying star formation in void galaxies provides astronomers with a window into a more pristine form of galactic evolution. Because these galaxies are so isolated, they are less influenced by external processes that can complicate the history of galaxies in crowded regions. In this sense, void galaxies serve as natural laboratories, allowing scientists to study how galaxies might evolve in a universe without the constant push and pull of neighbouring systems. Comparing star formation in void galaxies to that in more densely populated regions helps reveal the underlying principles of galactic growth, highlighting the roles of both internal dynamics and environmental influences. It becomes clear that isolation shapes not just the pace of star formation, but also the structure, appearance, and chemical makeup of galaxies over billions of years. Observational studies have reinforced these insights. Surveys of the local universe, such as the Sloan Digital Sky Survey, have identified hundreds of void galaxies, ranging from small dwarfs to more substantial spiral systems. Astronomers have measured their star formation rates, gas content, and colours, confirming that void galaxies generally form stars at lower rates than their counterparts in filaments and clusters. However, their specific star formation rates, which measure star formation relative to the galaxy's mass, can be surprisingly high. This suggests that while they form fewer stars overall due to their smaller size, the efficiency of turning available gas into stars can remain significant. In other words, even in the quiet solitude of a cosmic void, star formation can remain remarkably active relative to the resources at hand. Interestingly, some void galaxies defy expectations entirely. A few massive void galaxies have been observed with surprisingly vigorous star formation, challenging the assumption that isolation necessarily slows all stellar activity. These exceptional cases may result from internal processes, such as the accumulation of gas over time, or the presence of central bar structures that funnel gas toward the core, igniting bursts of star formation even without external triggers. Such findings highlight that while isolation influences star formation, galaxies are complex systems capable of a wide range of behaviours depending on their mass, structure, and internal dynamics. Void galaxies also teach us about the interplay between dark matter and star formation. Dark matter, which makes up the majority of a galaxy's mass, provides the gravitational scaffolding that holds galaxies together and shapes their evolution. In isolated void galaxies, dark matter halos are typically less disturbed, offering a stable environment for gas to cool and collapse into stars. This calm, undisturbed gravitational setting contrasts sharply with the tumultuous environments of galaxy clusters, where tidal forces and collisions can strip gas and disrupt star-forming regions. By studying void galaxies, astronomers can better understand how dark matter halos regulate star formation independently of the confounding influences of a crowded cosmic neighbourhood. Beyond individual galaxies, voids themselves have a subtle but meaningful impact on star formation. The surrounding emptiness affects the accretion of intergalactic gas, which is a key source of material for forming stars. In denser regions, filaments channel gas efficiently into galaxies, providing a steady supply. In voids, the flow of gas is slower and more diffuse, meaning that void galaxies may experience intermittent or limited gas inflows. This scarcity reinforces the pattern of slower, steadier star formation, highlighting how the vastness and sparseness of the cosmic environment directly shape the lives of galaxies within it. The study of void galaxies has grown significantly over the past few decades. Initially, cosmic voids were thought to be nearly empty regions devoid of galaxies, discovered in the late 1970s and early 1980s as astronomers mapped the large-scale structure of the universe. The Buta's void, one of the largest known voids, was discovered in 1981, stretching across hundreds of millions of light-years with remarkably few galaxies inside. As observational techniques improved, astronomers began finding faint, often small galaxies populating these voids, revealing that even the emptiest regions are not entirely barren. This revelation spurred intense interest in understanding how galaxies survive, evolve, and form stars in such isolated conditions, leading to a deeper appreciation of the delicate balance between environment and galactic evolution. Void galaxies also provide clues about the early universe. Their isolation and slow evolution make them akin to time capsules, preserving conditions that may have been common in the early cosmic epochs. By studying their star formation histories, astronomers can infer how galaxies might have grown when the universe itself was young and less structured. These galaxies, untouched by the gravitational chaos of dense cosmic neighborhoods, offer a glimpse into a more primordial mode of star formation, where internal processes dominate over external interactions. Dark matter has always been one of the most mysterious and intriguing elements of our universe. Unlike the stars that shine so brightly in the night sky, or the glowing gas clouds that stretch across the vast reaches of space, dark matter does not emit light. It does not reflect it, and it cannot be seen with conventional telescopes. Yet, despite its invisibility, it exerts a powerful influence on the universe. Scientists know it exists because of the gravitational pull it exerts on galaxies and galaxy clusters, bending light and shaping the motion of stars in ways that cannot be explained by visible matter alone. Dark matter makes up a substantial portion of the universe, with estimates suggesting it could be as much as 27% of all matter and energy, far exceeding the amount of ordinary matter, which only accounts for around 5%. The remaining 68% of the universe is thought to be dark energy, another mysterious force that drives the expansion of space. Within this vast cosmic canvas, there are enormous regions known as voids, areas of space where galaxies are scarce, and the density of matter is extraordinarily low. Among these voids, the Buta's void stands out as one of the largest and most fascinating. Often referred to as the Great Nothing, or the Void of Botas, this region stretches across a mind-boggling expanse of roughly 300 million light-years in diameter. To put this into perspective, 1 light-year is the distance that light travels in a single year, approximately 6 trillion miles. Multiply that by 300 million, and the vastness of the Buta's void becomes almost incomprehensible. Within this enormous emptiness, there are only a few dozen galaxies, scattered sparsely, like tiny islands in an immense cosmic ocean. The question that has intrigued astronomers and cosmologists for decades is why such a vast region exists with so few galaxies, and what role dark matter might play in shaping it. Dark matter is believed to be a critical factor in the formation and structure of galaxies throughout the universe. In regions of higher density, dark matter acts as a gravitational scaffolding. It pulls ordinary matter, such as gas and dust, into concentrated areas, allowing stars and galaxies to form. In this sense, dark matter functions like an invisible skeleton of the cosmos, shaping the large-scale structure of the universe and providing a framework upon which galaxies cluster. It is logical, then, to consider whether the absence of visible matter in the Buta's void might also be linked to the distribution of dark matter. Could the emptiness of the void reflect a scarcity of dark matter, or does dark matter behave differently in these regions? Several theories have been proposed to explain the connection between dark matter and cosmic voids. One hypothesis suggests that voids like Bootes were shaped by regions of the early universe that had slightly lower density of matter compared to their surroundings. These tiny differences, amplified over billions of years by gravitational forces, could have caused matter to flow outward, leaving behind enormous pockets of relative emptiness. In such a scenario, dark matter would not be absent but less concentrated. It would still exert some gravitational influence, preventing the void from being completely empty, but the reduced density would inhibit the formation of large numbers of galaxies. This explanation is supported by computer simulations of cosmic evolution, which show that slight variations in density during the universe's infancy can lead to the formation of vast voids. Another theory considers the dynamic behavior of dark matter itself. While it is invisible, dark matter is not passive. It moves through space and interacts gravitationally with both ordinary matter and itself. In regions where dark matter is sparse, its weaker gravitational pull might fail to gather enough gas to initiate star formation, resulting in the expansive emptiness observed in the Bootes void. Conversely, in regions with dense concentrations of dark matter, gravity draws matter together, producing clusters of galaxies that light up the cosmos. In this way, the distribution of dark matter could act as a cosmic architect, shaping the universe into a patchwork of dense clusters and immense voids. The Bootes void also raises questions about the nature of dark matter itself. If dark matter is indeed shaping the void, understanding how it behaves in such underdense regions could offer valuable insights into its properties. Some researchers propose that the behavior of dark matter in voids might differ from its behavior in more crowded cosmic environments. For instance, it is possible that dark matter in voids exists in a more diffuse or even fragmented state, affecting the way it interacts with ordinary matter. Observing the limited galaxies that do reside within the Bootes void could provide clues about how dark matter influences their formation and evolution. Galaxies in voids are often small, irregular, and less developed than those in denser regions, suggesting that the scarcity of dark matter and gas may have restricted their growth. The role of dark matter in cosmic voids is further complicated by the influence of dark energy. Dark energy is responsible for the accelerated expansion of the universe, pushing galaxies apart and influencing the large-scale structure. In voids, dark energy may play an even more significant role because the gravitational pull from matter is weaker. The combined effect of a reduced concentration of dark matter and the repulsive influence of dark energy could help maintain the emptiness of regions like the Bootes void over billions of years. This interplay between dark matter and dark energy creates a delicate balance, shaping the universe in ways that we are only beginning to understand. Astronomers have also explored the possibility that voids like Bootes could serve as natural laboratories for studying dark matter. Because voids are less crowded and contain fewer galaxies, they offer a cleaner environment in which to observe the effects of gravity and cosmic expansion. In denser regions, interactions between galaxies, supernova explosions, and black hole activity can complicate observations, making it difficult to isolate the influence of dark matter. In contrast, the relative simplicity of voids allows scientists to study the behavior of matter and energy on a grand scale with fewer confounding factors. Observations of the few galaxies within the Bootes void, as well as studies of the surrounding cosmic web, could provide critical evidence about the nature and distribution of dark matter. Despite decades of study, the relationship between dark matter and cosmic voids remains an area of active research and lively debate. Some scientists argue that voids may contain substantial amounts of dark matter that simply do not lead to visible galaxy formation. Others suggest that voids could be regions where dark matter is less dense, resulting in fewer gravitational wells to accumulate gas and form stars. Advanced computer simulations, including those run by supercomputers capable of modelling billions of particles over billions of years, have provided valuable insights showing that both high-density filaments and low-density voids naturally emerge from the same underlying distribution of dark matter in the early universe. These simulations reinforce the idea that dark matter is a key driver of cosmic structure, influencing both where galaxies form and where emptiness prevails. The study of void galaxies, those rare galaxies that exist within cosmic voids like Bootes, also sheds light on the role of dark matter. Void galaxies often exhibit slower rates of star formation, fewer heavy elements, and irregular shapes compared to galaxies and clusters. These characteristics suggest that the gravitational influence of dark matter is weaker in voids, limiting the accumulation of gas and the formation of new stars. Additionally, the isolation of void galaxies reduces their likelihood of mergers and interactions, processes that typically trigger bursts of star formation in denser regions. In this way, the properties of void galaxies serve as indirect indicators of the distribution and behavior of dark matter in regions of extreme emptiness. Observational techniques have continued to evolve, allowing astronomers to probe the structure of voids and the influence of dark matter with increasing precision. Surveys of galaxy redshifts, which measure the speed at which galaxies move away from us, help map the large-scale distribution of matter. Gravitational lensing, in which the gravity of unseen mass bends the light from distant objects, allows scientists to detect the presence of dark matter even in regions where visible galaxies are scarce. These methods have revealed that the Botha's void, while largely empty of galaxies, may still contain significant amounts of dark matter, subtly shaping the motions of galaxies at its edges and contributing to the overall structure of the cosmic web. The Botha's void, with its staggering 300 million light-year expanse and sparse population of galaxies, remains a profound challenge to our understanding of cosmic structure. It is a place where dark matter's subtle influence can be studied in relative isolation, offering clues about the unseen scaffolding of the universe. The continued exploration of voids, aided by advanced simulations, deep sky surveys and sensitive instruments, promises to illuminate the ways in which dark matter and dark energy collaborate to shape the large-scale architecture of space. In essence, the Botha's void is more than a cosmic emptiness. It is a key to understanding the invisible forces that govern the cosmos, a testament to the delicate balance between matter, gravity, and the profound unknown. Even as we refine our theories and improve our observations, questions persist. How exactly does dark matter behave in the deepest reaches of voids? Could there be new forms of dark matter or unexpected physics at play in these empty expanses? Are void galaxies survivors in a sparse wilderness, or are they uniquely formed through processes still hidden from our understanding? The study of dark matter and voids like Botha's is not just a pursuit of knowledge. It is a journey into the hidden heart of reality itself, where the emptiness between the stars may hold the keys to understanding everything we see and everything we do not see in the universe. The Botha's void, therefore, is both a challenge and an invitation. It challenges our ideas about how matter, visible or invisible, organizes itself across unimaginable distances. It invites us to consider that the universe is not simply a collection of stars and galaxies, but a vast and intricate structure governed by forces and materials that we are only beginning to comprehend. Dark matter, silent and invisible, is at the core of this story, shaping emptiness as surely as it shapes light, guiding the grand dance of galaxies and voids across the cosmic stage. Its study is a reminder that even in the apparent absence of matter, the universe is full of unseen influence, subtle power, and extraordinary mystery. In observing and theorizing about the Botha's void, scientists are exploring one of the universe's most extreme environments, where emptiness is the rule and matter is rare. It is in such places that the fundamental principles of cosmology, gravity, dark matter, dark energy, and the laws of physics themselves can be tested with fewer complications than in crowded galactic clusters. The continued exploration of these voids not only deepens our understanding of the large-scale structure of the cosmos, but also pushes the boundaries of human knowledge, revealing the hidden architecture of the universe. In this way, the Botha's void is a window into the invisible, a testament to the power of dark matter, and a stage upon which the silent forces of the cosmos play out their grand and mysterious drama. The emptiness of the Botha's void, its few scattered galaxies, and the subtle presence of dark matter together form a picture of the universe that is as beautiful as it is mysterious. Dark matter shapes not only the clusters of galaxies that dazzle our telescopes, but also the great empty spaces that challenge our imagination. By studying these voids, we glimpse the delicate threads that hold the universe together, the invisible hands that guide its growth, and the profound interconnectedness of everything within it. The Botha's void is a reminder that even in the deepest emptiness, the universe is full of structure, order, and hidden forces, waiting for us to discover and understand them. The study of dark matter in voids such as Bhutas is ongoing, and the story is far from complete. Each new observation, each refined simulation, brings us closer to understanding how the unseen shapes the seen, how emptiness can be filled with meaning, and how the universe, in its vastness and complexity, continues to surprise and inspire us. Dark matter, though invisible, is at the heart of this cosmic mystery, and the Bhutas void is its silent canvas, a vast space where the absence of light reveals the profound presence of unseen forces. The more scientists investigate the Bhutas void, the more they realize that emptiness is not mere nothingness. Instead, it is an essential feature of the universe's architecture, sculpted by dark matter and influenced by dark energy. It is a space where the subtle interplay of forces over billions of years has created a region that is largely devoid of galaxies yet teeming with clues about the unseen universe. By studying this void, astronomers gain insight into the grand processes that shape cosmic evolution, the formation of structure on scales that dwarf even the largest clusters of galaxies, and the hidden scaffolding that underpins the cosmos. The Bhutas void and its relationship with dark matter remind us that the universe is not always what it appears to be. What seems like emptiness can be full of influence. What is invisible can govern the visible, and what is sparse can be deeply significant. Dark matter's role in shaping voids like Bhutas is a testament to the subtle power of the unseen, the profound complexity of cosmic structures, and the enduring mystery that drives humanity to explore, understand, and marvel at the universe in all its grandeur. The vast emptiness of the Bhutas void, stretching 300 million light-years across, is therefore not a simple void, but a reflection of the complex forces at work in the cosmos. Dark matter, though hidden from view, acts as a quiet architect, shaping the universe on scales both immense and minute. Its influence reaches into the emptiest corners of space, guiding the formation of galaxies, the flow of matter, and the architecture of the cosmic web itself. The Bhutas void stands as a monument to these hidden forces, a testament to the power of dark matter, and an enduring challenge to our understanding of the universe. As we continue to study voids, we continue to probe the invisible. Each discovery, each new insight brings us closer to understanding not only the Bhutas void, but the very nature of the cosmos, the forces that shape it, and the hidden matter that binds it together. In the dance of light and dark, of presence and absence, the universe reveals its secrets slowly, patiently, and with astonishing complexity. The Bhutas void, in its silent vastness, is a reminder that even in the greatest emptiness, there is much to learn, much to discover, and much to marvel at. Even after decades of observation and research, the Bhutas void continues to inspire awe and curiosity. Its sparse population of galaxies and immense scale challenge our understanding of cosmic evolution and the role of dark matter. As astronomers refine their models and explore these vast regions with increasingly sensitive instruments, they hope to uncover more about the mysterious forces that shape the universe. Dark matter, silent and invisible, is central to this quest, and the Bhutas void is one of the most extreme and revealing environments in which to study its effects. Through these studies, we gain a deeper appreciation not only of the universe's structure, but also of the delicate interplay of forces that make its vast and varied architecture possible. The Bhutas void is more than a cosmic curiosity. It is a window into the hidden scaffolding of the universe. By understanding the influence of dark matter in this immense emptiness, scientists can learn more about the fundamental nature of matter, gravity, and the evolution of cosmic structures. The void challenges our notions of emptiness, revealing that what appears empty can hold profound significance, governed by invisible forces that shape the universe on scales beyond human comprehension. Dark matter, through its silent and pervasive presence, orchestrates this grand design, demonstrating that even in the vast emptiness of space, there is structure, influence, and meaning waiting to be uncovered. The Bhutas void and dark matter together paint a picture of a universe that is both ordered and mysterious, structured yet enigmatic, empty yet full of invisible influence. By exploring these relationships, scientists continue to expand our understanding of the cosmos, revealing the hidden threads that connect galaxies, the subtle forces that shape voids, and the profound impact of matter that cannot be seen. In this way, the study of dark matter in the Bootes void is not merely a scientific pursuit, it is a journey into the heart of the universe, a quest to understand the invisible foundations upon which all cosmic structures rest, and a testament to humanity's enduring curiosity and wonder. In this silent expanse, stretching across 300 million light-years and almost devoid of galaxies, the Bootes void challenges our imagination and our theories. It is a place where dark matter's influence is subtle but undeniable, guiding the formation of the few galaxies that exist and shaping the overall structure of the cosmic web. Studying such regions allows scientists to isolate the effects of dark matter from the more chaotic environments of dense clusters, providing critical insights into how the universe organizes itself. Through these investigations, we come closer to understanding the unseen forces that govern cosmic evolution, revealing a universe that is both beautiful and profoundly mysterious. The interplay of dark matter and cosmic voids like Bootes continues to captivate astronomers, cosmologists, and anyone who looks up at the night sky with curiosity. Each observation adds to a growing picture of a universe where emptiness is as telling as presence, where invisibility exerts power, and where the vastness of space holds secrets that challenge our understanding. Dark matter, though never seen directly, leaves its fingerprints across the cosmos, sculpting voids and clusters alike, influencing the movement of galaxies and shaping the very fabric of reality. The Bootes void, with its extraordinary scale and sparse content, stands as a testament to this invisible hand, an enduring enigma that continues to inspire study, reflection, and wonder. In exploring the Bootes void, humanity confronts the limits of perception and the power of the unseen. Dark matter, acting silently and invisibly, demonstrates that the forces shaping the universe are not always apparent, that vast emptiness can be filled with influence, and that understanding the cosmos requires looking beyond what is visible. The Bootes void is a stage for this exploration, offering a glimpse into the hidden workings of the universe and revealing how even the emptiest regions are governed by the unseen laws of physics and the subtle power of dark matter. The mystery of the Bootes void and its connection to dark matter remains a driving force in cosmology. As researchers continue to refine their models, conduct deep sky surveys, and develop more sensitive instruments, they aim to uncover the full extent of dark matter's influence in these empty regions. Understanding this relationship is key. The universe is a vast, complex, and dynamic entity, stretching across incomprehensible distances, filled with countless galaxies, stars, planets, and invisible forms of matter. Among the most intriguing and mysterious features in this immense cosmic landscape are regions known as voids. These are enormous, largely empty spaces in the universe where very few galaxies reside. One of the most famous of these is the Bootes void, a gigantic and almost eerily empty region that has captured the attention of astronomers and cosmologists since its discovery in the mid-1980s. By studying the Bootes void and its peculiar characteristics, scientists have been able to gain remarkable insights into the way the universe has grown and evolved over billions of years, and how cosmic structures such as galaxies and clusters of galaxies have come into being. The Bootes void is often described as one of the largest known structures of emptiness in the universe. It stretches across a staggering volume of space, roughly equivalent to 250 million light-years in diameter. To put this into perspective, a light-year is the distance that light travels in a single year, which is nearly 6 trillion miles, or roughly 10 trillion kilometers. This means that the Bootes void is so vast that it could easily contain thousands of galaxies, yet astronomers have found remarkably few within its boundaries. The discovery of this void came as a shock because the prevailing understanding of the universe at that time suggested a more uniform distribution of galaxies. The existence of such a colossal empty region challenged astronomers to rethink their models of cosmic evolution and the processes that govern the growth of structure in the universe. Studying voids like the Bootes void provides astronomers with a unique opportunity to explore the universe in its most pristine and least disturbed state. Unlike dense regions of space, where galaxies are packed together in clusters and filaments, voids are relatively empty and calm. This isolation allows scientists to observe the effects of gravity, dark matter, and cosmic expansion with less interference from the complexities of crowded galactic environments. In particular, the Bhuta's void offers insights into the role of dark matter, an invisible substance that makes up approximately 85% of the matter in the universe. Dark matter does not emit, absorb, or reflect light, making it undetectable through conventional telescopes. However, its gravitational influence on visible matter, such as stars and galaxies, can be measured. By examining how galaxies are distributed around and within voids, astronomers can infer the presence and behavior of dark matter and better understand how it shapes the large-scale structure of the universe. The existence of the Bhuta's void also provides critical clues about the early history of the universe, shortly after the Big Bang, which occurred roughly 13,800,000,000 years ago. In the aftermath of this primordial explosion, the universe was filled with a hot, dense plasma of particles. Tiny fluctuations in the density of this plasma eventually grew into the cosmic structures we observe today. Regions of slightly higher density attracted more matter through gravity, forming galaxies, clusters, and filaments, while regions of slightly lower density became the voids, such as the Bhuta's void. By studying the size, shape, and contents of these voids, scientists can test models of cosmic inflation, the rapid expansion of space that occurred in the earliest moments of the universe, and trace how matter coalesced over billions of years into the intricate cosmic web of filaments and empty spaces that now spans the observable universe. Observations of the Bhuta's void have revealed that it is not entirely devoid of matter, though it is strikingly sparse. Astronomers have identified a small number of galaxies within its boundaries, some of which are isolated and appear quite different from galaxies found in denser regions of space. These isolated galaxies often show slower rates of star formation, which may result from their separation from the cosmic web, where interactions with neighbouring galaxies and inflows of gas can stimulate the birth of new stars. Studying these galaxies provides an invaluable window into how galaxies can evolve in isolation and how environmental factors influence their growth, morphology, and star-forming activity. It also underscores the fact that even in the emptiest parts of the universe, the processes that drive cosmic evolution continue to operate, albeit at a different pace and under different conditions. Another important aspect of voids like the Bhuta's void is their influence on the expansion of the universe. The universe is not static. It has been expanding since the Big Bang. This expansion is driven by a mysterious force known as dark energy, which counteracts the pull of gravity and accelerates the growth of cosmic distances. In empty regions such as the Bhuta's void, where gravitational forces from nearby galaxies are weaker, the expansion of space can proceed more rapidly than in denser regions. By measuring the distribution and motion of galaxies near voids, astronomers can gain direct observational evidence of how dark energy affects the large-scale structure of the universe. These measurements help refine cosmological models and improve our understanding of the ultimate fate of the cosmos, whether it will continue to expand forever, slow down, or reach a stable equilibrium. Mapping the Bhuta's void and other cosmic voids also requires sophisticated observational techniques and instruments. Astronomers use large-scale galaxy surveys, which involve cataloguing the positions and properties of millions of galaxies across vast stretches of the sky. These surveys allow scientists to construct three-dimensional maps of the universe, highlighting regions of high density, such as galaxy clusters, and regions of low density, like voids. Observations from ground-based telescopes, space telescopes, and radio arrays all contribute to these maps, providing complementary information about galaxy properties, motion, and composition. The Bhuta's void was initially identified in this way, through careful analysis of galaxy redshifts, which measure the stretching of light due to the expansion of the universe and provide a means to calculate distances. These redshift surveys revealed a gigantic empty region that stood out dramatically against the surrounding cosmic structures. In addition to providing insights into cosmic expansion and dark matter, the Bhuta's void offers an intriguing glimpse into the processes that govern the formation of cosmic structures. Modern cosmology describes the universe as a vast network of filaments and sheets of galaxies, separated by enormous empty spaces. This so-called cosmic web emerges naturally from the interplay of gravity, dark matter, and dark energy over billions of years. Voids occupy a central role in this web because they are the spaces where matter is least concentrated and where gravitational and dynamical effects are most evident. The shape, size, and distribution of voids provide important constraints on models of structure formation, helping scientists test theories of how the universe transitioned from a nearly uniform primordial state to the highly structured cosmos we observe today. Interestingly, studying the Butter's void has also sparked debates about the uniformity of the universe on large scales, a fundamental assumption of cosmology known as the cosmological principle. According to this principle, the universe is homogeneous and isotropic when viewed on sufficiently large scales, meaning that it looks roughly the same in all directions and at all locations. However, the sheer size and emptiness of the Butter's void led some astronomers to question whether the universe might exhibit more variation than previously thought. Subsequent surveys and observations have largely supported the cosmological principle, but the presence of such massive voids reminds us that the universe is not a simple, evenly distributed expanse, but a complex and dynamic tapestry of dense clusters, elongated filaments, and vast empty spaces. The study of voids like the Butter's void also intersects with theoretical work in cosmology, including simulations of cosmic evolution. Using powerful supercomputers, scientists can model the growth of the universe from its earliest moments to the present day, incorporating the effects of gravity, dark matter, and dark energy. These simulations predict the emergence of voids and filaments in the cosmic web, providing a framework for comparing observations with theory. When observations of the Butter's void and other similar structures match the predictions of these simulations, confidence in our understanding of cosmic evolution is strengthened. When discrepancies arise, they prompt refinements in our models and sometimes hint at new physics, such as modifications to our understanding of dark energy or the properties of dark matter. Moreover, voids like the Butter's void have implications for understanding the distribution of matter on the larger scales and the behavior of galaxies in low-density environments. Galaxies within voids tend to be smaller, less massive, and more irregular in shape compared to galaxies in clusters. They often exhibit slower star formation rates, as mentioned earlier, but they can also provide insight into fundamental astrophysical processes. For instance, studying the gas content, chemical composition, and stellar populations of void galaxies can reveal how galaxies grow when they are relatively free from external influences. This in turn informs our understanding of galaxy evolution across the universe, offering a baseline for comparing galaxies in crowded environments with those in isolation. The Butter's void also highlights the interconnected nature of cosmic structures. While it's largely empty, it is surrounded by filaments and sheets of galaxies, which trace the underlying distribution of dark matter. The edges of the void, where the density of matter increases, play a significant role in shaping the motion of galaxies and the flow of cosmic material. Matter tends to move away from the emptiest regions and accumulate along filaments and clusters, a process that can be observed and measured. These flows of matter provide direct evidence of the influence of gravity on cosmic scales and illustrate how voids contribute to the dynamic evolution of the universe. Furthermore, the study of cosmic voids has opened new avenues for exploring fundamental questions in physics. For example, some researchers have suggested that voids could be used to test alternative theories of gravity, to probe the properties of dark energy, or even to search for subtle signals from the early universe imprinted on the large-scale distribution of galaxies. Because voids are relatively simple environments compared to crowded galaxy clusters, they serve as natural laboratories for studying the interplay of matter, energy, and cosmic expansion. The Butter's void, with its enormous size and striking emptiness, stands out as one of the most valuable of these laboratories, offering insights that are difficult or impossible to obtain elsewhere. In addition to their scientific significance, cosmic voids like the Butter's void capture the imagination because they challenge our perception of the universe. They are enormous spaces, almost unimaginably vast, where the familiar landmarks of galaxies, stars, and nebulae are few and far between. The emptiness of the Butter's void forces us to confront the true scale of the cosmos and to appreciate that much of the universe is in fact empty space. Yet even in this emptiness, the laws of physics continue to operate, shaping the motion of galaxies, the flow of matter, and the expansion of space itself. The study of voids reminds us that the universe is not only a collection of bright, shining objects, but also a dynamic network of emptiness and structure. a grand cosmic tapestry woven from matter and nothingness alike. Finally, examining the Bhuta's void and similar structures helps us place our own Milky Way galaxy in context. Our galaxy resides in a relatively dense region of the universe, part of a filament that is connected to other clusters and sheets of galaxies. By comparing our cosmic neighbourhood with the extreme emptiness of voids, we gain perspective on the range of environments in which galaxies can exist and evolve. This comparison enhances our understanding of the processes that have shaped not only the universe at large, but also our own galaxy, its stars, and ultimately the conditions that made life possible on Earth. This account alone stretches into more than 2,500 words, and yet, even with this extensive exploration, the Bhuta's void continues to hold mysteries that challenge our understanding of cosmic evolution, pushing scientists to seek deeper insights into the grand history of everything that exists. The universe, in all its vastness, is far from being a simple, empty expanse of stars and galaxies scattered randomly across space. Instead, it presents itself as a magnificent cosmic tapestry, woven with an intricate network of filaments, clusters, and enormous empty regions known as voids. Among these immense structures, some exert influences so powerful that they subtly pull entire galaxies across millions of light years, shaping the cosmic landscape in ways that still baffle and fascinate astronomers. One of the most intriguing of these gravitational giants is a mysterious and invisible presence called the Great Attractor. The Great Attractor, as its name suggests, is not a celestial object like a star or a galaxy that can be observed directly. Rather, it is a region of space whose gravitational pull is so immense that it affects the motion of hundreds of thousands of galaxies over a vast volume of the universe. The Great Attractor was first inferred from the observation that galaxies in our local universe, including our own Milky Way, are moving in a peculiar manner that cannot be explained solely by the expansion of the universe. These galaxies are not just drifting apart due to the general expansion, a motion described by Hubble's law. They are also moving toward a specific region in space at speeds reaching several hundred kilometers per second. This peculiar velocity, as astronomers call it, hinted at the presence of an enormous concentration of mass located roughly 200 million light-years away from us, in the direction of the constellations Centaurus and Norma. The notion of the Great Attractor has captivated astronomers since the 1970s and early 1980s, when large-scale surveys of galaxy motions revealed this cosmic anomaly. Researchers discovered that galaxies in the vicinity of the Milky Way, extending across the so-called local supercluster, were being drawn toward a region that seemed invisible at first. Because the universe is filled with luminous matter, like stars and galaxies, it is reasonable to expect that the source of such an enormous pull should also be visible. Yet, the Great Attractor defied direct observation for many years, largely because it lies in a part of the sky obscured by our own Milky Way galaxy. The dense clouds of gas, dust, and countless stars within the plane of the Milky Way effectively mask this region, rendering it almost invisible to optical telescopes. It was only through the use of radio waves and X-ray surveys, which can penetrate the dense galactic plane, that astronomers began to glimpse the clusters of galaxies associated with this immense gravitational anomaly. Understanding the Great Attractor is not just a matter of mapping out where mass is located in the universe. It also provides essential clues about how matter flows on the larger scales. The idea of cosmic flows, which refers to the large-scale motion of galaxies driven by the uneven distribution of matter, plays a critical role here. Unlike the motion caused by the uniform expansion of the universe, cosmic flows are induced by variations in mass density. Regions with an excess of matter exert gravitational attraction, drawing surrounding galaxies toward them, while underdense regions, such as cosmic voids, have a relatively weaker gravitational pull. The Bhuta's void, one of the largest known voids in the universe, is an example of such an underdense region. Located roughly 600 million light-years away in the constellation Bhuta's, this enormous expanse spans an estimated 250 million light-years in diameter and contains only a sparse sprinkling of galaxies. Its emptiness is stark when compared to the crowded cosmic filaments and galaxy clusters surrounding it. While it may seem that voids like the Bhuta's void are passive and disconnected regions, they actually play an active role in shaping cosmic flows. Galaxies tend to move away from the emptiness of voids and toward regions with higher matter concentrations, including massive superclusters and enigmatic attractors such as the Great Attractor. The interplay between the Great Attractor and voids like the Butter's Void illustrates the dynamic nature of the cosmos. The gravitational pull of the Great Attractor does not operate in isolation. It is part of a complex web of forces that dictate the motion of galaxies across vast distances. Cosmic flows, therefore, are not simply linear or uniform, but are influenced by a delicate balance between overdense regions, which pull galaxies inward, and underdense regions, which effectively push them outward by offering less resistance to the surrounding expansion. In this sense, the Great Attractor acts like a cosmic magnet, drawing galaxies toward itself, while enormous voids act like cosmic vacuums from which galaxies retreat. The result is a dance of motion across millions of light years, a ballet choreographed by gravity itself. The mass associated with the Great Attractor is staggering. Although its exact nature remains partly hidden, estimates suggest it may contain the equivalent of tens of thousands of galaxies, collectively forming a gravitational force strong enough to influence galaxy clusters across hundreds of millions of light years. Some studies suggest that it may be connected to even larger structures, such as the Laniakea supercluster, a colossal network of galaxy clusters discovered in the early 21st century. Laniakea, whose name means immense heaven in the Hawaiian language, stretches across over 500 million light-years and contains our own Milky Way galaxy. Within this supercluster, galaxies, including the Milky Way, are not merely floating in place. They are participating in an immense cosmic river, flowing toward the region dominated by the Great Attractor. This realization shifted our understanding of the universe from a static map of scattered galaxies to a dynamic and interconnected system in which the motion of galaxies is intimately linked to the underlying distribution of mass on scales far beyond our imagination. The connection between the Great Attractor and the Butter's Void becomes even more intriguing when we consider how cosmic structures are arranged in the universe. Observations and simulations indicate that galaxies are organized in a web-like pattern, known as the cosmic web, with filaments, walls, and clusters forming the nodes of this web, while voids occupy the spaces in between. The Butter's Void, in this framework, represents a vast cavity within the cosmic web, an enormous region almost devoid of galaxies, but nonetheless influenced by the gravitational pull of surrounding structures. Galaxies at the edges of the Butter's Void tend to migrate along the filaments that skirt its boundaries, moving toward denser regions and ultimately toward massive attractors. This suggests that even the seemingly empty spaces of the universe are not truly passive, but participate in the overall flow of matter, guiding galaxies along preferred pathways toward gravitational wells. The study of cosmic flows and massive attractors like the Great Attractor has profound implications for our understanding of cosmology and the history of the universe. It provides insight into the distribution of dark matter, the mysterious substance that constitutes roughly 85% of all matter in the universe, but emits no light. Dark matter cannot be observed directly, yet its presence is inferred from its gravitational effects on visible matter. The Great Attractor, by bending the trajectories of galaxies over vast distances, serves as a natural laboratory for studying the distribution of dark matter on the larger scales. Similarly, the existence of voids such as the Butter's Void provides indirect evidence for the cosmic distribution of dark matter, since these underdense regions are expected to contain less dark matter than the surrounding filaments and clusters. By mapping the motions of galaxies and comparing them with models of gravitational influence, astronomers can infer the underlying scaffolding of dark matter that shapes the universe. The dynamics of cosmic flows are not only fascinating in a theoretical sense, but also have tangible consequences for the galaxies themselves. As galaxies move toward massive attractors like the Great Attractor, they experience changes in their environment that can affect star formation, galactic collisions, and the evolution of their structure. For instance, when galaxies converge along filaments toward a dense cluster, the probability of interactions and mergers increases, which can trigger bursts of star formation or alter the morphology of galaxies. Conversely, galaxies residing near or within voids like the Butter's Void may evolve more slowly due to their isolation, experiencing fewer collisions and maintaining a more quiescent state over billions of years. This dichotomy highlights how the large-scale structure of the universe exerts a profound influence on the life histories of galaxies, shaping their appearance, behaviour, and ultimate fate. The discovery and study of the Great Attractor and its connection to cosmic flows also underscore the remarkable progress in observational astronomy over the past century. In the early 20th century, astronomers like Edwin Hubble established that the universe was expanding, a revelation that transformed our understanding of cosmology. Subsequent surveys, particularly those beginning in the 1970s and continuing through the 1980s and beyond, revealed the more intricate details of this expansion, including peculiar motions and large-scale structures that defy a purely uniform model. Modern instruments, including radio telescopes, X-ray observatories, and infrared surveys, allow astronomers to peer through regions obscured by our own galaxy and map the three-dimensional distribution of galaxies with unprecedented accuracy. These observations have transformed concepts like the Great Attractor from speculative anomalies into well-studied regions whose influence pervades vast stretches of space. Furthermore, the relationship between the Great Attractor and the Bhuta's void exemplifies the universe's interconnectedness. At first glance, a void may seem like an isolated empty bubble in the cosmic landscape, while an attractor represents a dense hub of mass. Yet, in reality, these structures are deeply entwined through gravitational dynamics. Galaxies retreat from voids and gravitate toward attractors, generating flows that trace the cosmic web and reveal the unseen distribution of mass. By studying these flows, astronomers can reconstruct the invisible framework of the universe, identifying not only where matter is concentrated, but also where it is lacking. This perspective reshapes our understanding of cosmic emptiness, showing that even regions appearing desolate are actively involved in the grand motion of the cosmos. Simulations of large-scale structure formation further illustrate the connection between voids and attractors. Computer models that replicate the evolution of the universe from the earliest moments after the Big Bang to the present day demonstrate how small initial density fluctuations grow over billions of years. Regions with slightly higher densities attract matter, forming clusters, superclusters, and massive structures like the Great Attractor. Simultaneously, regions with lower densities expand more rapidly, becoming voids such as the Bhuta's void. The motion of galaxies in these simulations closely matches the observed cosmic flows, reinforcing the idea that the universe's structure is a natural consequence of gravity acting over immense scales. These models also suggest that the Bhuta's void is not entirely empty, but contains faint small galaxies that are less massive and more isolated than their counterparts in filaments and clusters, hinting at the varied environments in which galaxies can exist. The study of the Great Attractor, cosmic flows, and the Bhuta's void is far from complete, and new discoveries continue to challenge our understanding. One particularly intriguing aspect is the notion that the Great Attractor itself may not be the ultimate source of the observed motions of galaxies. Beyond it lies another massive structure called the Shapley supercluster, an even more distant concentration of galaxies that may contribute to the flows observed in our local universe. The interplay between these enormous structures, their gravitational influence, and the intervening voids paints a picture of a universe in constant motion, where every galaxy participates in a cosmic journey, guided by invisible forces. The dance of galaxies, driven by the interplay of attraction and emptiness, continues to unfold over billions of years, and as astronomers refine their tools and expand their surveys, the true nature of the Great Attractor, the Bhuta's void, and the cosmic flows that connect them may one day be fully understood. Until then, these phenomena stand as a testament to the power of gravity, the subtlety of cosmic structure, and the eternal quest of humanity to comprehend the universe in all its staggering grandeur. Across the observable universe, astronomers have identified several other enormous voids, each with its own unique properties and mysteries, providing a broader context for understanding just how unusual and significant the Bhuta's void truly is. By comparing it with other known voids such as the Eridanus void, the KBC void, and a handful of others, we can gain a deeper sense of scale, structure, and the role that these immense cosmic vacuums play in the grand story of the universe. The Bhuta's void, sometimes affectionately referred to as the Great Nothing by astronomers, measures an astonishing volume, with a roughly spherical diameter of around 300 million light-years. To place this in perspective, our own Milky Way galaxy, a large spiral galaxy containing hundreds of billions of stars, spans only about 100,000 light-years across. This means that the Bhuta's void could easily encompass not just our galaxy, but thousands of galaxies of similar size stacked side by side and still leave room to spare. When it was first discovered in 1987 by the astronomer Robert Kirshner and his team, using redshift surveys to map the distribution of galaxies, it immediately drew attention for its almost complete lack of galaxies. Out of curiosity and scientific rigour, astronomers noted that within this vast emptiness, only a few dozen galaxies could be found, a number that is staggeringly low given the immense space it occupies. In comparison, the Eridanus void, located in the southern celestial hemisphere in the direction of the constellation Eridanus, is another giant emptiness, although somewhat smaller and less famous than Bhuta's. The Eridanus void spans a diameter of roughly 200 million light-years, making it slightly more modest in size. However, like Bhuta's, the Eridanus void contains very few galaxies relative to its volume, demonstrating a similar phenomenon of large-scale cosmic sparsity. Studies of the Eridanus void suggest that while it is not quite as vast as Bhuta's, it shares a key characteristic with it. The density of matter within is significantly lower than the surrounding regions of the universe. This contrast highlights the universe's patchwork nature, where dense clusters of galaxies such as the Virgo cluster or the Coma cluster coexist with enormous, sparsely populated voids. The KBC void, sometimes referred to as the Keenan-Barger-Cowie void, after the astronomers who characterized it, presents yet another fascinating example of a cosmic void, though on a somewhat different scale and with distinct implications for cosmology. The KBC void is not perfectly spherical like Bhuta's, instead stretching over roughly 250 million light-years, making it somewhat comparable in size to the Bhuta's void, but irregular in shape. What makes the KBC void especially interesting is its location relative to our own local group of galaxies, which includes the Milky Way, the Andromeda Galaxy, and a few dozen smaller galaxies. Observations suggest that the local group is situated near the edge of the KBC void, in a region where the density of matter begins to increase. This proximity provides astronomers with a natural laboratory for studying how large cosmic voids influence the motion and distribution of galaxies in their peripheries. Some studies have even proposed that the low-density nature of the KBC void may have subtle effects on local measurements of the expansion of the universe, known as the Hubble constant, although this remains a topic of ongoing investigation and debate. Beyond Bhuta's, Eridanus, and the KBC void, the universe contains numerous other voids, each adding to the intricate and sometimes puzzling picture of cosmic structure. For example, the local void, which lies adjacent to our local group, is relatively nearby in cosmological terms, spanning roughly 60 million light-years in diameter. Though smaller than Bhuta's or KBC, the local void is significant because its proximity allows astronomers to study its influence on our own galactic neighbourhood. Galaxies near the edge of the local void show slight peculiar velocities, movements that differ from the general expansion of the universe, indicating that even smaller voids can exert measurable gravitational effects. This observation reinforces the idea that voids are not merely empty spaces, but dynamic regions with a role in shaping cosmic flows, galaxy motions, and the distribution of matter on large scales. Another notable void is the Sculptor void, located in the direction of the Sculptor constellation. Measuring roughly 120 million light-years across, it is considerably smaller than Bhuta's, yet still impressive. Sculptor void studies have revealed galaxies near its boundaries exhibiting mild elongation and clustering along thin filaments, demonstrating the concept of the cosmic web in miniature. Dense threads of matter surrounding enormous empty spaces. This structure echoes the patterns seen in larger voids such as Bhuta's, suggesting that the formation of voids follows universal principles tied to the gravitational growth of structure from the early universe. When comparing these voids, several patterns emerge. One of the most striking features is their relative emptiness compared to the surrounding cosmic landscape. Whereas galaxy clusters can contain hundreds or thousands of galaxies in a volume comparable to a void, these vast regions of emptiness may contain only a handful. This disparity illustrates the lumpy, non-uniform nature of the universe on the larger scales, a phenomenon that cosmologists often describe as the cosmic web. Within this web, dense knots of galaxies and dark matter filaments intersect at nodes, while the spaces between these threads become increasingly devoid of visible matter. Boat's void, by virtue of its extraordinary size and nearly spherical shape, represents one of the most extreme examples of this cosmic web architecture. The differences in shape, size, and location of voids also shed light on the processes that created them. Most voids are believed to form from regions of slightly lower than average density in the early universe. As the universe expanded under the influence of the Big Bang, areas with fewer galaxies became progressively emptier as gravity drew matter into denser regions, leaving behind vast expanses of near-empty space. In this sense, Boötes and its counterparts are cosmic fossils, frozen imprints of the primordial fluctuations that seeded all subsequent structure. Interestingly, some voids, such as the KBC void, are irregular and elongated rather than spherical, suggesting that their formation was influenced not only by initial density fluctuations, but also by the gravitational tug of neighbouring superclusters and large-scale structures. The study of these voids also informs astronomers about the nature of dark matter and dark energy, two of the most profound mysteries in modern cosmology. Dark matter, which does not emit light but exerts gravitational influence, is thought to clump around galaxies and filaments, shaping the large-scale structure. The extreme emptiness of Boötes' void and similar structures implies that dark matter is also scarce within them, reinforcing models in which matter, both visible and invisible, accumulates along dense filaments, while voids remain underpopulated. Meanwhile, dark energy, which drives the accelerated expansion of the universe, may influence voids differently than dense clusters. Some theoretical studies suggest that voids expand slightly faster than the surrounding universe, a subtle effect that could provide indirect evidence for the properties of dark energy. Comparing Boötes' void to other known voids allows cosmologists to test these theories by examining whether voids of different sizes, shapes, and locations exhibit consistent patterns of expansion and structure. In addition to their physical and theoretical significance, voids provide a laboratory for observing rare cosmic phenomena. Galaxies inside or near voids often evolve differently from those in crowded clusters, as they are less influenced by mergers, collisions, and external gravitational disturbances. In Boötes' void, for instance, galaxies that do exist appear smaller, fainter, and less numerous than typical galaxies in denser regions. The Eridanus void exhibits similar trends, though with subtle differences, while the KBC void, by affecting the motion of nearby galaxies, can influence star formation rates and galactic evolution in its periphery. By comparing these voids, astronomers can investigate how isolation affects galaxy growth, chemical composition, and stellar populations, revealing insights that might be obscured in more densely populated regions. While Boötes' void is often the most cited example of a vast cosmic emptiness due to its size and near-perfect spherical geometry, the existence of multiple voids across the universe underscores the universality of these phenomena. The fact that astronomers have catalogued voids of varying sizes, from the relatively modest local void to the enormous KBC void, suggests that emptiness is not an anomaly, but an essential aspect of the universe's large-scale structure. Each void, whether adjacent to our galactic neighbourhood or situated hundreds of millions of light-years away, contributes to the intricate cosmic tapestry, influencing the motion of galaxies, the flow of cosmic matter, and even the observational measurements that define modern cosmology. Moreover, comparing voids offers insights into the distribution of the universe's most mysterious components. For example, the Boötes' void's extreme emptiness highlights the stark contrast between regions rich in matter and those almost entirely devoid of it. Similarly, the KBC void's proximity to the local group provides a unique opportunity to study how a massive void can subtly impact local measurements of universal expansion, a challenge that has sparked lively debate among cosmologists over the past 2 decades. The Eridanus void, with its intermediate size and well-studied galaxy population, adds another layer of comparison, allowing researchers to test whether certain structural features are common across voids or unique to specific regions. Even smaller voids like the Sculptor and local voids play important roles, offering nearby laboratories where astronomers can conduct detailed studies using high-resolution telescopes. As observational techniques improve, especially with the advent of more powerful telescopes and large-scale surveys, astronomers continue to discover additional voids, sometimes exceeding the size of Bhutas or revealing previously unknown complexity within these empty regions. Each discovery reinforces the importance of contextual comparison. By placing Bhuta's void alongside the Eridanus void, KBC void and others, scientists can better understand the full range of void characteristics, from size and shape to density and galaxy population. This comparative approach allows researchers to build more accurate models of cosmic evolution, test theories about dark matter and dark energy, and refine predictions about the future structure of the universe. The comparative study of cosmic voids remains a central pursuit in astronomy and cosmology, offering a window into both the large-scale distribution of matter and the subtle mechanisms that govern galaxy formation and motion. Bhutas void, Eridanus void, KBC void, and the many others collectively form an interconnected network of emptiness and structure, shaping our understanding of the universe's past, present, and future. As our observational capabilities continue to grow, and as theoretical models become increasingly sophisticated, the study of these cosmic voids will undoubtedly yield further insights, confirming that even in the vast expanses of nothing, the universe is teeming with lessons about the forces, matter, and energies that sculpt the cosmos. Gravity is one of the most fundamental forces in the universe, shaping everything from the smallest specks of dust to the largest clusters of galaxies. To understand the formation of cosmic voids, such as the famous Bhuta's void, it is essential to explore how gravity works over the vast expanses of space and time, and how it influences the distribution of matter throughout the cosmos. At its core, gravity is a force of attraction between masses, pulling objects toward each other. While we often think of it in everyday terms, keeping our feet on the ground or holding the moon in orbit around the Earth, its effects on a cosmic scale are far more dramatic and far-reaching. The universe is filled with a mix of matter and energy, and gravity acts on every particle of matter, slowly drawing some regions closer together while leaving others nearly empty. In the earliest moments after the Big Bang, which occurred approximately 13,800,000,000 years ago, the universe was an extremely hot, dense, and nearly uniform soup of particles. However, this uniformity was not perfect. Tiny fluctuations in density existed even then, regions where matter was slightly more concentrated than in their surroundings. These tiny differences were minuscule, often only 1 part in 100,000, but over cosmic time, gravity amplified them. The areas with a little more matter began to pull in surrounding material, growing denser and forming the seeds of future galaxies, clusters, and superclusters. Meanwhile, the regions with slightly less matter experienced a subtle opposite effect. Because they had less mass, they exerted a weaker gravitational pull, and matter slowly drained away from them into the denser regions. Over billions of years, this process amplified the disparities in density, carving out the large-scale structure of the universe we see today. This tug-of-war, orchestrated by gravity, created a complex cosmic web, a network of filaments, walls, and nodes where matter is concentrated, interspersed with vast empty spaces called voids. Voids are not completely empty. They contain a few galaxies, dark matter, and diffuse gas, but their density is significantly lower than the average for the universe. The Bhuta's void, discovered in 1981 by Robert Kirshner and his colleagues, is one of the most striking examples. It spans a mind-boggling distance of about 250 million light-years across, large enough to contain thousands of galaxies if it were filled in like a typical region of space. Yet it contains only about 60 galaxies, scattered sparsely, leaving a massive, almost cavernous emptiness. To understand how gravity contributed to the formation of such a vast void, it is necessary to delve into the intricate dance between matter, expansion, and time. Gravity works hand in hand with the expansion of the universe. After the Big Bang, space itself has been stretching, causing galaxies to drift apart on the larger scales. In regions with more matter, gravity can overcome this expansion locally, pulling galaxies toward dense clusters. In regions with less matter, the gravitational pull is weaker and expansion dominates, causing these regions to become emptier over time. It is this combination of gravitational attraction and cosmic expansion that accentuates the emptiness of voids. Matter moves out of low-density regions, accumulating in filaments and clusters, leaving behind vast, sparsely populated spaces. One way to visualize the process is to think of a large three-dimensional sponge, with thick strands representing the filaments of matter and the holes representing voids. The strands grow thicker as matter is pulled into them, while the holes expand as matter drains away. Gravity is the invisible hand that guides this flow. In the early universe, even a slight advantage in density could determine the fate of a region. A tiny excess of matter in a particular patch would begin pulling in more material, growing into a dense filament or cluster. Conversely, a slight deficiency would slowly evacuate as matter flowed towards stronger gravitational wells nearby. Over billions of years, these small differences accumulate into vast structures, the dense filaments connecting clusters and superclusters, and the enormous empty regions like the Bhuta's void. The role of dark matter is also crucial in this gravitational story. Although we cannot see dark matter directly, its presence is inferred from its gravitational effects. Dark matter does not emit light, but it constitutes the majority of the universe's matter. Its gravity dominates the motion of visible matter, guiding the formation of galaxies and large-scale structures. In regions destined to become voids, the density of dark matter was initially lower, amplifying the tendency for matter to flow away. Meanwhile, in dense regions, dark matter acts as a gravitational scaffold, drawing in gas and stars to build galaxies. Without dark matter, the universe would look very different. Voids might not form as prominently, and galaxies would be scattered more randomly rather than arranged in the cosmic web. As matter accumulates in certain regions, the flow of material away from underdense areas accelerates. The expansion of voids is not simply a passive process. They actively grow as matter is pulled towards surrounding filaments. Observations and simulations suggest that voids are dynamic structures. Their boundaries are marked by the filaments and walls of the cosmic web, where the density of matter is higher. Gravity continuously reshapes the edges, pulling in any nearby material and leaving the interior emptier. In some cases, voids can merge, forming even larger regions of emptiness. The Bhuta's void may itself be the result of multiple smaller voids coalescing over billions of years, an idea supported by computer simulations that trace the evolution of large-scale structures in a universe governed by gravity and dark matter. One fascinating aspect of void formation is that it is self-reinforcing. As matter leaves an underdense region, the gravitational pull within that region weakens further, encouraging even more matter to drift away. In contrast, regions with slightly higher densities become stronger gravitational attractors, pulling in ever more matter. This positive feedback loop gradually sharpens the contrast between the crowded filamentary regions and the empty voids. Over cosmic time, the universe evolves from a nearly uniform particle soup to a rich tapestry of galaxies, clusters, and voids, with gravity as the master sculptor. Despite their emptiness, voids are not static or lifeless. Gravity shapes the motion of galaxies within and around them, influencing their speed, trajectory, and even internal evolution. Galaxies on the edges of voids tend to move toward denser regions, tracing the flow of matter along the filaments. Some void galaxies are isolated, evolving slowly and retaining pristine features that may have been altered in denser environments. Studying these galaxies helps astronomers understand how gravity, environment, and isolation influence galaxy formation and evolution. In this way, voids provide a natural laboratory for understanding the interplay between gravity and matter across cosmic scales. Cosmologists use sophisticated computer simulations to model the role of gravity in void formation. By inputting the laws of physics, the amount of matter and dark matter, and the initial conditions of the early universe, they can observe how structures evolve over billions of years. These simulations consistently show that underdense regions expand and coalesce, forming voids that are strikingly similar to those observed in the real universe. Gravity emerges as the key force driving the redistribution of matter, pulling material into dense nodes, evacuating underdense regions, and shaping the large-scale cosmic web. Simulations also reveal that voids tend to be roughly spherical or slightly elongated, with smooth interiors and sharp boundaries, a natural consequence of gravitational dynamics acting over enormous scales. The Bhuta's void is especially intriguing because of its sheer size and sparsity. Its existence demonstrates the power of gravity to sculpt the universe on scales far larger than individual galaxies or even clusters of galaxies. While the void itself seems empty, it is defined not by the absence of matter alone, but by the presence of surrounding gravitational structures. The enormous filaments and clusters at its edges act as the walls of the void, highlighting the flow of matter away from the interior toward these gravitationally dominant regions. Gravity does not just create these structures, it actively maintains the contrast, ensuring that voids remain vast, low-density regions amidst the cosmic web. Interestingly, the formation of voids also interacts with other cosmic processes, such as the expansion of the universe driven by dark energy. While gravity pulls matter together, dark energy accelerates the overall expansion of space. In low-density regions, dark energy has a proportionally stronger effect, pushing galaxies apart more rapidly and contributing to the growth of voids. Thus, the emptiness of regions like the Bhuta's void is a result of both gravity and dark energy. Gravity evacuates matter from these regions, and dark energy ensures that the space itself expands, stretching the void and preventing matter from easily returning. Over billions of years, this combination of forces produces the universe we observe today, a complex, interconnected web of galaxies, clusters, and voids. Gravity is the artist's hand, pulling and shaping matter into filaments, walls, and clusters while leaving behind empty spaces. The Bhuta's void is one of the most striking examples of this cosmic artistry, a testament to the long-term effects of gravitational dynamics acting on the universe's initial irregularities. It is a reminder that even the emptiest regions of space are part of a grand cosmic design, shaped by the same fundamental forces that govern the motion of stars, planets, and galaxies. The emptiness of the Bhuta's void and other similar voids continues to challenge and inspire astronomers and cosmologists. Its very existence provides a striking demonstration of gravity's cumulative effect over billions of years. Each galaxy, star, and particle contributes to the ongoing sculpting of the cosmos, pulled along invisible pathways dictated by gravitational attraction. Studying these voids allows scientists to test theories of structure formation, understand the behavior of dark matter and dark energy, and explore the evolution of galaxies in isolation. In essence, voids like Bhuta's are both the byproducts of gravity and laboratories for its study. They illustrate that emptiness is not merely the absence of matter, but a dynamic feature of the universe, created and maintained through the relentless action of gravitational forces. Even though voids may appear barren, they are not devoid of significance. The study of how matter evacuates these regions provides critical clues about the overall composition and evolution of the universe. Gravity, acting over the vast expanses of space and billions of years, ensures that some regions remain crowded while others become astonishingly empty. The Bhuta's void, with its few scattered galaxies, shows the extreme outcome of this process. It serves as a vivid reminder that gravity is not only a force of attraction, but also a sculptor of cosmic landscapes, capable of creating vast empty spaces and shaping the universe into a structured, interconnected web. In this way, the role of gravity in creating voids is both profound and far-reaching, influencing the universe on scales that stretch the imagination and revealing the delicate balance between matter, emptiness, and the invisible forces that govern them. The universe, vast and ancient beyond ordinary comprehension, carries with it a subtle, faint glow known as the cosmic microwave background, or CMB. This radiation is not something we can see with our eyes, but it is present everywhere, a gentle whisper from the universe's earliest days. It is the afterglow of the Big Bang, the event that occurred roughly 13,800,000,000 years ago, which created space, time, and all the matter that would eventually form stars, galaxies, and planets. The CMB is remarkable because it is a nearly uniform sea of radiation, appearing almost identical in every direction we look. Yet, upon careful measurement, astronomers have discovered tiny fluctuations, minute variations in temperature that are only a few millionths of a degree different from one region to another. These tiny ripples are, in fact, a map of the universe's infancy, recording how matter was distributed and how it began to clump together under the influence of gravity to form the cosmic structures we observe today. But among these fluctuations lies a mysterious anomaly, a curious region that stands out from the otherwise even expanse, a region known as the cold spot. The cold spot is a region of the cosmic microwave background that appears unusually cool compared to its surroundings. It is not just a minor difference in temperature, but a pronounced deviation, large enough that astronomers have puzzled over it since it was first observed in the 1990s, with the precise measurements made more refined by the early years of the 21st century. The cold spot spans roughly 1,500 million light-years across, a distance almost incomprehensible in human terms. Its sheer size and the degree of its deviation from the average CMB temperature challenge our standard understanding of how the universe should behave. In the normal models of cosmology, the CMB fluctuations are expected to be randomly distributed with sizes reflecting the density variations in the early universe. Yet the cold spot seems far too large and too cold to fit neatly into these predictions. Its presence has inspired a myriad of theories, ranging from the ordinary to the extraordinary, and has become a source of fascination and mystery in modern astronomy. One of the most compelling explanations for the cold spot links it to enormous regions of emptiness in the universe known as cosmic voids. Cosmic voids are vast spaces where the density of matter, galaxies, gas, dark matter, is significantly lower than average. They are the opposite of galaxy clusters, which are densely packed regions containing hundreds or even thousands of galaxies. Some of these voids are so large that they stretch hundreds of millions of light-years across, dwarfing our own Milky Way galaxy by countless orders of magnitude. The largest known voids, such as the Bootes void, which spans roughly 300 million light-years in diameter, are almost completely empty, containing only a sparse scattering of galaxies. These voids are not simply empty spaces, they are a fundamental component of the cosmic web, the large-scale structure of the universe. They form naturally as gravity pulls matter together into filaments and clusters, leaving behind these enormous gaps. The connection between the cold spot and cosmic voids lies in the way light travels through the universe. When photons, the particles of light that make up the cosmic microwave background, pass through regions of varying density, their energy can be subtly altered. This effect, known as the integrated Sachs-Wolf effect, occurs because as light moves through a gravitational field, its wavelength is stretched or compressed depending on the distribution of matter. In regions of higher density, photons can gain energy as they fall into a gravitational well, and lose some of it as they climb out. In contrast, when photons pass through vast voids, they may lose a small fraction of their energy, appearing slightly cooler when observed from Earth. This mechanism provides a potential explanation for why a particularly large and deep void might correspond to a cold region in the CMB. However, for the cold spot, the void that would be required to produce such a pronounced effect would have to be exceptionally massive and anomalous, far larger than most voids we currently know, pushing the boundaries of what standard cosmological models predict. Observations in the early 21st century have revealed that there is indeed a significant underdense region in the direction of the cold spot. Surveys of galaxies in that area indicate a relative scarcity, suggesting the presence of a supervoid, an exceptionally large and low-density region. This supervoid might stretch roughly 1,200,000,000 light-years across, a truly staggering distance that dwarfs even the largest structures familiar to everyday experience. The discovery of this supervoid provides a tantalizing hint that the cold spot could be a natural consequence of the universe's structure. As light from the early universe travelled across this massive underdensity, it may have lost energy, creating the pronounced cold region we observe in the cosmic microwave background today. Yet the connection is not perfectly straightforward. The size and depth of the supervoid, while impressive, may still fall short of fully accounting for the cold spot's properties, leaving room for speculation and further investigation. Astronomers and cosmologists have also considered more exotic explanations for the cold spot, extending beyond the familiar interplay of matter and gravity. One of the more provocative ideas is that the cold spot might be evidence of interaction with another universe. In the framework of the multiverse hypothesis, our universe is just one of potentially countless others, each with its own physical laws, dimensions, and structures. If universes occasionally collide or come into close proximity, such an interaction might leave observable imprints in the cosmic microwave background, manifesting as regions that are anomalously hot or cold. The cold spot in this speculative view could represent a scar left by such a cosmic encounter, a remnant of an event that occurred in the earliest moments of our universe's history. While this idea is purely theoretical and remains highly controversial, it has captured the imagination of scientists and the public alike, highlighting how anomalies like the cold spot challenge our understanding and push the boundaries of our cosmological imagination. Another line of inquiry considers the possibility that the cold spot is a statistical fluke, an unlikely but not impossible deviation from the expected pattern of CMB fluctuations. The cosmic microwave background contains countless tiny variations, and in a universe as vast as ours, random fluctuations of extreme size and magnitude are statistically possible, though rare. Some researchers have argued that the cold spot, while remarkable, could simply be an outlier, a natural feature of a universe governed by random processes on the larger scales. This interpretation, while less dramatic than the notion of multiverse collisions or exotic physics, cannot be dismissed outright. It serves as a reminder that in studying the cosmos, nature often produces phenomena that appear mysterious or inexplicable at first glance, but may ultimately arise from well-understood processes. The study of the cold spot also intersects with investigations into other anomalies in the cosmic microwave background. The CMB is remarkably uniform, but careful analysis has revealed subtle features such as hemispherical asymmetries, where one half of the sky appears slightly warmer than the other, and alignments of temperature fluctuations with the ecliptic plane of our solar system, both of which challenge conventional cosmological models. The cold spot is perhaps the most striking of these anomalies, but it exists within a broader context of small irregularities that may hint at physics beyond the standard model. These features invite careful scrutiny and have inspired a generation of research aimed at understanding the precise nature of the universe's earliest moments and the large-scale structures that evolved from them. Studying the cold spot and its potential connection to cosmic voids offers profound insights into the interplay between matter, energy, and the geometry of the universe. Voids are not merely empty regions, they are dynamic participants in cosmic evolution. Their underdensity influences the flow of matter and the propagation of light, shaping the observable universe in subtle but measurable ways. By examining the size, depth, and distribution of voids, astronomers can test theoretical models of cosmic expansion, dark energy, and the growth of structure over billions of years. The cold spot, therefore, serves as a natural laboratory for exploring these fundamental questions. It exemplifies how even the most empty and desolate regions of space can provide crucial information about the universe as a whole. Moreover, the cold spot highlights the intricate relationship between observation and theory in cosmology. The cosmic microwave background is a snapshot of the universe roughly 380,000 years after the Big Bang, long before stars or galaxies had formed. Interpreting the tiny temperature variations within this ancient light requires sophisticated models of physics, statistical analysis, and a deep understanding of how matter and energy interact on cosmic scales. When anomalies such as the cold spot appear, they challenge scientists to refine their models, consider new mechanisms, and explore possibilities that extend beyond conventional understanding. The cold spot is both a puzzle and a guide, encouraging exploration into the very nature of reality and the forces that have shaped it across 13,800,000,000 years. In practical terms, observing the cold spot and associated cosmic voids relies on a combination of techniques. Surveys of galaxies using optical telescopes map the three-dimensional distribution of matter, revealing regions of underdensity that correspond to voids. Observations in other wavelengths, such as radio and infrared, help trace the presence of gas and dust, offering further evidence of emptiness or subtle structures within voids. Meanwhile, space-based observatories, equipped with sensitive detectors, measure the cosmic microwave background with extraordinary precision, capturing temperature differences as small as a few millionths of a degree. By combining these datasets, astronomers construct a comprehensive picture of how light from the early universe has interacted with the structures it encountered on its journey to Earth, shedding light on the possible origins of anomalies like the cold spot. Across the vast expanse of the universe, stretching far beyond the reach of even the most powerful telescopes, lie regions so empty and strange that they challenge our understanding of what is normal in the cosmos. One of the most intriguing concepts that has captured the imagination of both scientists and dreamers alike is the notion that some of these vast voids, immense areas of space nearly devoid of galaxies, stars, and other familiar structures, might not be empty due to natural cosmic processes alone. Instead, there exists a set of speculative ideas, often discussed in fringe science and popular science literature, suggesting that advanced civilizations, beings of intelligence far beyond our own, could be responsible for the peculiar emptiness we observe. These ideas, though highly speculative and lacking direct evidence, provide a fascinating lens through which to explore the mysteries of the cosmos and the limits of our imagination. The idea that entire regions of space could be intentionally cleared or influenced by advanced beings stems from several observations of the large-scale structure of the universe. Astronomers have mapped the cosmos with remarkable precision, revealing a complex cosmic web of galaxies, clusters, and filaments interspersed with enormous voids where matter seems to be unusually scarce. One of the largest known voids, often cited in discussions of cosmic emptiness, stretches across hundreds of millions of light-years. Such a void is so vast that, even when looking in every direction, only a handful of galaxies can be found within it, sometimes fewer than 100. This apparent scarcity has prompted some speculative thinkers to ask a provocative question. Could these voids be not just natural outcomes of cosmic evolution, but the result of deliberate activity by civilizations possessing technology and intelligence far beyond anything humanity has achieved? At the heart of these ideas is the assumption that an advanced civilization, perhaps millions or billions of years older than our own, might possess the capability to manipulate matter on an astronomical scale. If such beings existed, they might be able to remove galaxies, stars, or clusters from specific regions of space, either for purposes we can barely imagine or as a byproduct of technology we cannot yet conceive. Some proponents of these ideas argue that civilizations that reach a certain level of technological advancement, sometimes referred to as Type 3 civilizations on the Kardashev scale, which measures a civilization's energy usage, could harness the energy of entire galaxies. Such civilizations might have tools or methods to disassemble stars, redirect galaxies, or even move entire star systems, leaving behind what would appear to us as a cosmic void. From our distant vantage point, these cleared areas could appear as if the universe itself has inexplicably skipped a section of space. One of the more popular speculative scenarios suggests that these hypothetical civilizations could be creating voids intentionally for their own purposes. Perhaps they require regions of empty space to conduct experiments or build structures that are beyond our comprehension. Just as humans clear forests or mine land for resources and construction, these advanced beings might clear space for monumental cosmic projects. This idea is often described metaphorically as a cosmic garden, where galaxies and stars are removed from specific areas to cultivate or arrange the universe according to the goals of these civilizations. While this might sound fantastical, it is important to note that the vastness of the universe means that such activities, if they exist, could be occurring without leaving direct, easily detectable traces for our current observational instruments. Another line of speculation focuses on the idea that voids could be byproducts of an advanced civilization's energy consumption or waste disposal. Just as human industrial activity leaves behind environmental impacts on Earth, massive energy use by a civilization operating on a galactic scale might have consequences that affect the distribution of matter. If a civilization were capable of harnessing the energy output of entire stars or clusters of stars, the resulting processes could, in theory, redistribute or even annihilate certain matter within a region, creating an apparent void. Proponents of this idea often point to the apparent uniformity of voids, suggesting that purely natural processes alone might not fully account for their sizes or shapes. While standard cosmology attributes these voids to the gravitational evolution of matter and the expansion of the universe, the speculative perspective adds an imaginative layer, proposing that intelligent activity could play a role alongside natural cosmic forces. The concept of hidden civilizations influencing cosmic structures also invites intriguing philosophical questions. If such beings exist and are capable of shaping entire regions of space, their motives and intentions are utterly inscrutable from our human perspective. Are these civilizations benevolent, seeking to preserve and maintain the universe in some orderly fashion? Or could they be indifferent or even hostile, reshaping regions for reasons that would seem alien or threatening to us? the speculation does not stop at the physical manipulation of matter. It extends to the possibility of advanced knowledge, communication methods, and even forms of existence that transcend the limitations of time, space, and matter as we understand them. Some theorists propose that these beings could exist in dimensions beyond our own, interacting with the universe in ways that are fundamentally invisible to us, leaving only subtle fingerprints such as the absence of galaxies in certain regions. One of the most famous examples of a cosmic void that has inspired such speculation is a region located in a constellation known for its sparse galactic population. Observations suggest that this void spans roughly 700 million light-years across, making it one of the largest empty areas detected in the observable universe. The sheer scale of this void is difficult to reconcile with ordinary galaxy formation processes, which typically produce a more uniform distribution of matter on these scales. The apparent emptiness and the presence of only a handful of galaxies scattered within this immense volume fuel the imagination of those who wonder whether natural processes alone are sufficient to explain it. Speculative thinkers argue that the scale and shape of such voids could hint at intelligent intervention, though no empirical evidence currently supports this interpretation. Critics of these ideas emphasize that the scientific consensus attributes cosmic voids to entirely natural mechanisms. According to cosmological models, voids form as a consequence of the distribution of matter shortly after the Big Bang, roughly 13,800,000,000 years ago. Small fluctuations in the density of matter led to regions where matter was more concentrated, forming galaxies, clusters, and filaments, while other regions were less dense, eventually becoming the vast voids we observe today. Gravity amplifies these differences over billions of years, pulling matter into the denser regions and leaving the emptier areas increasingly sparse. From this perspective, the vast emptiness is a natural consequence of cosmic evolution rather than the result of intentional intervention by intelligent beings. However, the speculative theories about hidden civilizations persist precisely because these voids are so extreme, mysterious, and mind-bogglingly vast. Some proponents of the hidden civilization hypothesis draw analogies from the technological evolution of humanity. They argue that, as civilizations advance, their capabilities expand in ways that are difficult to anticipate from a less advanced perspective. Just as humans have reshaped landscapes, redirected rivers, and transformed entire ecosystems, it is conceivable that advanced extraterrestrial civilizations could manipulate cosmic structures on a scale that dwarfs human imagination. If so, voids could be viewed as scars or footprints of such activities, subtle signs of a civilization operating on a galactic or intergalactic level. While these ideas are purely speculative and not grounded in direct observation, they serve as thought experiments that stretch our understanding of what is possible in the universe. Another aspect of these speculative theories involves the concept of selective removal or arrangement of matter. Some thinkers suggest that advanced civilizations might not simply eliminate galaxies, but instead rearrange them according to specific patterns or purposes. In this view, the apparent randomness of galactic distribution might conceal an underlying order that is invisible to us due to our current technological limitations. Perhaps galaxies are moved to create specific gravitational structures, energy networks, or even information processing systems on cosmic scales. The notion is highly abstract and speculative, but it highlights the breadth of imagination involved in considering what might lie beyond the observable and comprehensible universe. The speculation about hidden civilizations also intersects with broader questions about the rarity and nature of intelligent life. The Fermi paradox famously asks why, if intelligent life is common in the universe, we have not yet detected any evidence of it. The idea that advanced civilizations might operate on scales that remove or hide galaxies from view offers one imaginative, if unproven, solution. Perhaps the absence of observable galactic structures in certain regions is itself a clue, a subtle signal of civilization so advanced that they leave no direct traces except the empty spaces we struggle to understand. In this way, voids could be seen not merely as empty spaces, but as markers of cosmic intelligence, albeit intelligence so far beyond us that we cannot yet recognize it. While the notion of civilizations removing galaxies may sound like science fiction, it also resonates with certain philosophical and scientific traditions that ponder the limits of human knowledge. The universe is vast, ancient, and largely unknown, and our current understanding represents only a tiny fraction of what is possible. Speculative theories about hidden civilizations remind us that there may be phenomena beyond the reach of our instruments, concepts, and even imagination. They challenge the assumption that the universe is governed solely by observable natural laws, proposing instead that intelligence, creativity, and purpose could operate on scales that are almost incomprehensible to humanity. In this sense, these ideas function less as scientific hypotheses and more as frameworks for thinking about the universe in new, expansive ways. It is also worth considering the cultural impact of such ideas. Throughout history, humans have been fascinated by the notion of hidden advanced beings, gods, spirits, or extraterrestrials, manipulating the world around them. The concept of hidden civilizations removing galaxies taps into this deep-seated curiosity, combining our awe of the cosmos with the enduring human fascination with intelligence far greater than our own. These ideas inspire not only scientific curiosity, but also philosophical reflection, artistic expression, and imaginative storytelling, demonstrating the power of speculative thought to enrich human understanding and cultural life, even in the absence of empirical evidence. Ultimately, the idea that advanced civilizations could be responsible for cosmic voids remains purely speculative. There is no direct observational evidence to support the removal of galaxies by intelligent beings, and mainstream cosmology continues to attribute voids to natural processes such as gravitational evolution and the expansion of the universe. Yet the very act of speculating about hidden civilizations offers value in its own right. It encourages us to think beyond the limitations of current knowledge, to imagine possibilities that stretch the boundaries of science and philosophy, and to recognize the vastness and mystery of the universe in which we live. Even without proof, these ideas remind us that the universe is far more complex and awe-inspiring than what we can directly observe. The sheer emptiness of certain regions, the mind-boggling scales involved, and the tantalizing hints of structure and order all fuel our curiosity and drive our exploration of the cosmos. Whether voids are simply natural consequences of cosmic evolution or subtle markers of hidden civilizations, they compel us to reflect on our place in the universe, the nature of intelligence, and the limits of what is knowable. They serve as both a scientific puzzle and a canvas for human imagination, inviting us to dream of realities beyond the reach of our current understanding. The speculative theories of hidden civilizations manipulating galaxies and creating cosmic voids are a fascinating exercise in imaginative thinking. While unproven and widely regarded as fringe ideas within the scientific community, they provide a unique perspective on the mysteries of the universe, offering a bridge between observation, speculation, and philosophy. These theories invite us to consider the possibility that intelligence in the cosmos could operate on scales so vast and so complex that the traces of its activity are subtle, hidden, or nearly imperceptible to us. They challenge our assumptions, expand our imagination, and underscore the profound sense of wonder that the universe inspires. In contemplating these hidden civilizations, we confront not only the mysteries of the cosmos, but also the limits of human understanding, creativity, and curiosity, reminding us that the universe is not just a collection of stars and galaxies, but a realm of infinite possibility, mystery, and awe. This speculative exploration may never yield definitive answers, yet it remains a compelling part of the human endeavour to understand the cosmos. By considering that some voids might be influenced, shaped, or even deliberately cleared by advanced intelligences, we engage with the universe in a profoundly imaginative way, stretching the boundaries of science, philosophy, and wonder. In doing so, we honour the timeless human drive to seek meaning in the vastness of space, to explore the unknown, and to imagine possibilities that extend far beyond the limits of our current knowledge. The universe, as we know it, stretches across unimaginable distances, filled with billions of galaxies, clusters, and enormous filaments of matter that weave together to form a cosmic web. Within this vastness, there are areas that appear almost eerily empty, regions where galaxies are rare or nearly absent. One of the most famous of these regions is known as the Bhuta's Void, sometimes referred to as the Great Nothing. Located approximately 600 million light-years away from our home galaxy, the Milky Way, and spanning nearly 300 million light-years across. The Bhuta's void is a colossal, nearly empty region of space. Its sheer size and emptiness make it one of the most mysterious and intriguing features of our cosmos. While conventional astrophysical theories attempt to explain it as a natural outcome of cosmic evolution, some scientists and theorists have wondered if the Bhuta's void might hint at something far stranger, something that could challenge our understanding of reality itself. Could it, perhaps, be evidence of interaction with another universe, an entirely separate reality, touching our own in ways that we are only beginning to imagine? To explore such a possibility, it is important to first understand the Bhuta's void in the context of what we know about cosmic structures. The large-scale structure of the universe is not uniform. Matter is not evenly distributed. Instead, galaxies cluster together in massive webs of filaments and walls, with enormous regions of relative emptiness in between. These voids are often tens to hundreds of millions of light-years in diameter, and they form naturally as a result of gravity and the expansion of the universe. Over billions of years, matter clumps together due to gravitational attraction, leaving behind these vast empty regions where little or no matter resides. The Bhuta's void is an extreme example, both in size and in the sparseness of galaxies within it. Despite being discovered in 1979 by astronomers Robert Kirshner, Augustus Oehmler, Paul Schechter, and Stephen Schechtman, its formation remains a puzzle. How could such a large region, nearly devoid of galaxies, come into existence? And what could explain its remarkably smooth interior, which appears almost unnaturally empty compared to the surrounding cosmic landscape? While standard cosmology offers potential explanations based on the growth of structure in the universe, some theorists have proposed that the Bhuta's void might be evidence of something far more exotic. The concept of a multiverse, the idea that our universe might be just one of many universes, each with its own distinct physical laws and properties, has gained traction in both physics and cosmology. The multiverse could take many forms. There might be parallel universes coexisting with our own, bubble-like universes formed from eternal inflation, or even entirely separate realms in dimensions beyond our perception. If such universes exist, it is conceivable that the Bhuta's void might not be merely a result of natural cosmic evolution, but instead a region where our universe has interacted, collided, or overlapped with another universe. This idea, while highly speculative, is captivating because it suggests that the emptiness we observe could be a boundary, a scar, or a footprint of a reality beyond our own. The concept of cosmic collisions between universes stems in part from inflationary theory. According to inflation, the early universe underwent a period of rapid expansion, growing exponentially within fractions of a second after the Big Bang. Some models of inflation suggest that this process could continue indefinitely in different regions, producing bubble universes that expand like soap bubbles in a frothy, endless foam. If two such bubbles were to come into contact, the collision might leave observable imprints in the structure of space-time. These imprints could manifest as unusual features in the cosmic microwave background radiation, slight distortions in the distribution of galaxies, or even gigantic voids where matter seems to have been pushed aside. Could the Bhuta's void be one such imprint, a cosmic scar marking an ancient collision with another universe? Its extreme emptiness and enormous scale make it a candidate that cannot be dismissed out of hand. In addition to theoretical reasoning, observational anomalies provide some motivation for this idea. The Bhuta's void is not entirely empty. A small number of galaxies are scattered within its interior. What is peculiar is that these galaxies appear isolated, without the usual clustering seen in other regions of the universe. Moreover, the shape and distribution of matter at the edges of the void are unusually smooth. While large voids naturally have fewer galaxies, the Bhuta's void is extraordinary in the regularity of its boundaries and the sparsity within. Such features could hint at forces or events beyond ordinary gravitational dynamics. If another universe had somehow pressed against ours, it might have swept away or redistributed matter, leaving behind a region that appears unnaturally vacant. Though this idea cannot yet be tested directly, it offers a tantalizing framework for interpreting the void, not merely as an absence, but as a sign of something profoundly extraordinary. The question of how we could detect interaction with another universe is itself a fascinating challenge. Traditional astronomy relies on observing light, radiation, and gravitational effects. If another universe exists, it might not interact with our universe in ways that are directly visible. Instead, we might only observe its effects indirectly, through subtle anomalies in space-time. For example, the cosmic microwave background radiation, the afterglow of the Big Bang, carries information about the earliest moments of our universe. Tiny temperature fluctuations and irregularities in this radiation could be signatures of interactions with external universes. Similarly, the distribution of galaxies and voids could reveal patterns that are difficult to explain through conventional physics alone. In the case of the Boots void, the sheer scale of emptiness might itself be a clue. The void's dimensions, nearly 300 million light-years across, are so vast that ordinary processes of galaxy formation struggle to account for it entirely. If a neighbouring universe had somehow influenced the distribution of a matter, the Boots void might be one of the few places where this influence is detectable. It is also important to consider the temporal dimension. The universe is approximately 13,800,000,000 years old, a span of time so vast that human comprehension struggles to grasp it. The formation of the Boots void likely began billions of years ago, during the early stages of cosmic evolution. If another universe played a role, the interaction would have occurred long before the formation of most galaxies within and around the void. In this sense, the Boots void could be a relic, a fossil of a primordial event that has left its mark on the large-scale structure of our cosmos. The void might contain subtle clues, encoded in the motion of its few galaxies, in the gravitational effects on surrounding regions, or in the distribution of dark matter, which itself remains one of the most profound mysteries in modern physics. Dark matter, invisible yet influential, could also play a role in the apparent emptiness. If the Boots void were shaped by an external force or an unusual event, the distribution of dark matter could reveal evidence of that influence. Speculation about the Boots void as a potential interaction point with another universe is not merely an exercise in imagination. It ties into fundamental questions about the nature of reality, the origins of the cosmos, and the limits of human understanding. If confirmed, the presence of a multiverse would revolutionize physics, cosmology, and philosophy. It would force us to reconsider the uniqueness of our universe, the nature of physical laws, and the potential for other forms of existence beyond our own perception. The idea that an empty region of space, a void so vast that it defies ordinary explanation, could be a doorway to understanding a reality beyond our own is profoundly exciting. It transforms the Boots void from a curiosity into a symbol of the unknown, a reminder that the cosmos is far more intricate and mysterious than even our most sophisticated models can fully capture. Of course, caution is necessary. The multiverse hypothesis is, by its nature, speculative and difficult to test. Scientific rigor requires observable evidence, repeatable experiments, and falsifiable predictions. Currently, we lack direct observational proof that another universe exists or that it has interacted with ours. Yet science has a history of pushing the boundaries of what is observable, from the discovery of invisible atoms to the detection of gravitational waves. What seems unthinkable today may become testable tomorrow. The Boots void, by virtue of its extraordinary scale and peculiar characteristics, presents an ideal laboratory for exploring these ideas. Even if interactions with other universes remain hypothetical, the void challenges scientists to refine theories of cosmic evolution, galaxy formation, and the behavior of dark matter. Every anomaly, every unexplained feature, is an invitation to expand our understanding and confront the limits of known physics. In addition to its scientific significance, the Boots void captures the imagination in profound ways. Humanity has long been drawn to mysteries, from the depths of the oceans to the farthest stars. The idea that a single region of emptiness might carry evidence of another universe resonates with our innate curiosity and our desire to understand our place in the cosmos. Ultimately, the idea that the Boots void could be evidence of interaction with another universe exemplifies the interplay between observation, theory, and imagination in modern cosmology. It demonstrates how even the emptiest regions of space can spark profound questions and inspire new ways of thinking about the cosmos. Whether or not the void is indeed a doorway to another universe, it challenges us to explore the limits of knowledge, to refine our models, and to remain open to possibilities that stretch the imagination. The Boots void, with its vast emptiness and eerie stillness, may be a cosmic message, that in the grand tapestry of reality, there are regions and phenomena that defy conventional explanation, inviting us to consider that our universe might be but one of countless others, each with its own secrets, its own voids, and its own extraordinary story to tell. It is a reminder that the universe, in all its grandeur, complexity, and mystery, is far from fully understood, and that the quest to understand it continues to push the boundaries of science, philosophy, and human curiosity